travel. For centuries, it has been both the greatest curiosity and the deepest fear of mankind, because bending time means challenging existence itself. From Einstein's equations to the vibrations of quantum fields, from the darkness of black holes to the split-second perception of the human brain, everything revolves around this question: does time really flow, or are we drifting through it? Perhaps the past and the future were never separate. We just chose to walk in one direction without realizing it. But as science advances, the line we say, "we can't go back," stretches a little more every year. Quantum entanglement, gravitational time differences, information paradoxes, they all whisper the same secret. Time is not a wall, but a structure. And those who understand that structure can rebuild not only the past, but also their own future. Maybe one day, it will be possible not to change the past, but to fix the future in advance. That's why this journey starts with awareness, not machines. Because to truly control time is to grasp the meaning, not the seconds. Now get ready, because we are about to embark on a journey, not in time, but in the depth of thought. If you are ready, let's start. By the way, if you like and subscribe to my video, that's the most effective way to support me. If you can tell me where in the world you are watching from and what time it is, I would love to read it in the comments. 1. Time dilation near extreme gravity can be engineered into a one-way time machine. Near a massive body, the rate of time slows compared with regions of weaker gravity. This is not metaphor, but a measured consequence of general relativity across many experiments and technologies. By placing a habitat or a laboratory deep within a strong gravitational field and maintaining safe orbits, inhabitants experience fewer ticks of proper time, while distant observers accumulate more. The effect compounds with proximity and mass, so that even a small difference in altitude can translate into measurable divergences once precision clocks and long durations are involved. A practical one-way machine emerges because the path down into gravity and back out again cannot pay back the lost rate. Travelers spend a short personal interval exploring or working near the massive source, while years pass for those who remain far away. The return brings them forward into a planetary future that unfolded without them. Crucially, no paradox arises because no signal or traveler moved backward along any world line. Each step followed forward causal order while exploiting how different world lines accrue different amounts of time. Engineering constraints define the feasibility. A deep well implies compact objects, such as neutron stars, or close orbits around a supermassive black hole, where tidal forces do not shred the vessel. Materials, radiation shielding, and navigation must tolerate intense fields and relativistic speeds if orbital stability demands fast motion. Autonomy and life support must bridge communication delays and maintain coherence of operations, while clock rates drift relative to mission control. Every subsystem becomes a clock, as temperature control, chemical reactions, and computation rates all rescale with the local rate of time. The payoff is profound. A civilization could send archivists, scientists, or even future-oriented trusts into slow-time vaults to harvest centuries of external progress after only a few local years. Medicine and cryogenic strategies could pair with gravitational time banking to extend subjective lifetimes. Cultural continuity and long bets gain a new tool, since institutions sheltered in slowed time can ride out volatile eras. The cost is asymmetry. The machine only moves travelers forward and returns them to a future that left them behind. 2. Rapid relativistic travel makes personal time detach from calendar time. High acceleration to near light speed stretches the duration experienced on board a ship, while the outside world races ahead. The physics is encoded in the Lorentz factor, which governs how moving clocks run slow and moving rulers contract. This mismatch requires no exotic matter and has already been validated with particles, atomic clocks on aircraft, and corrections inside satellite navigation. Scale the velocity to a significant fraction of light, and a voyage spanning a handful of shipboard years could correspond to decades or centuries on Earth. Such travel breaks the assumption that calendars are shared references. Two friends who part ways reunite with mismatched biographies. One may have accumulated deep knowledge and memories during a short journey while the planet rebuilt cities, altered languages, and rewrote laws during the same interval. Legal and ethical frameworks collapse under this wedge. Age, consent, pension rights, and even parental status become sensitive to world line length rather than birthdays. Economies must address arbitrage where investments made by slow travelers mature far beyond their subjective planning horizon. Propulsion is the hard limit. Chemical rockets cannot approach the required speeds without a ludicrous fuel fraction. Nuclear pulse, fusion torch, antimatter catalysis, and beamed sail concepts move the problem from fuel mass toward power generation and beam stability. Human physiology imposes additional barriers since prolonged acceleration stresses bodies and demands artificial gravity or rotational habitats. Radiation exposure from interstellar media at relativistic speeds becomes a central medical risk, so shielding and magnetic deflection must be integrated from the first sketch. If solved, relativistic travel becomes a cultural shock machine. Pilots leave during one art movement and return into a society that treats that movement as ancient history. Philosophies that tie identity to continuous social presence will strain, while philosophies that anchor identity in personal continuity will flourish. Education, memory, and heritage will be curated for travelers whose biographies decouple from the communal flow. The sense of progress shifts from a linear parade to a mosaic where individual timelines cross at angles rather than march side by side. 3. Rotating black holes twist space-time and may permit loops in time geometry. A rotating black hole drags space-time around with it. This frame dragging grows extreme near the ergosphere where nothing can remain at rest relative to distant stars. The geometry acquired by spinning mass is described by the Kerr solution, which differs fundamentally from the non-rotating case. Within certain mathematical extensions, trajectories can circle in ways that return to earlier coordinates of time, while never exceeding light speed locally. This is an invitation to imagine loops in time drawn entirely from the geometry of rotation. Physical access raises concerns. The idealized solution is smooth, while realistic black holes likely carry turbulence, accretion plasma, magnetic fields, and quantum fluctuations that erode the neat pathways required for coherent looping. Tidal forces must be managed so that any craft or signal can survive the gradients. The energy extraction, known as the Penrose process, indicates that rotation is a reservoir that can be tapped, which further suggests that time geometry near the ergosphere is not passive but dynamic under interaction. Even if loops exist, consistency becomes the guardian. A traveler who completes a loop must not set initial conditions that prevent the loop from forming. Models such as the Novikov principle enforce this by pruning histories that self-contradict. In practice, this would appear as improbable coincidences that steer actions into forms that complete the loop rather than break it. The mathematics allows closure, while the statistics become unfriendly to freedom in the naive sense. Observationally, the signatures to watch include quasi-periodic oscillations, polarization patterns, and timing irregularities in light near the event horizon. Very long baseline interferometry already images photon rings that test the Kerr metric. Any deviation that hints at non-trivial time geometry would provoke a new generation of experiments. The pragmatic view holds that loops may be mathematically available, yet physically inaccessible. The imaginative view holds that rotation is the first natural handle ever found on the structure of time. 4. Traversable wormholes stabilized by exotic matter could bridge different times. A wormhole connects distant regions through a short tunnel in space-time. Left to itself, the throat collapses too fast for passage. Negative energy density can keep the throat open by countering gravity. Quantum field theory allows fleeting negative energy in squeezed vacuum states, and within the Casimir effect, yet bounds known as quantum inequalities restrict the size and duration of such regions. The recipe is tantalizing. Combine geometry with exotic energy and a passage appears. Time travel enters when the two mouths undergo different histories of motion or gravity. Move one mouth at high speed and bring it back. The two mouths now disagree on elapsed time. A traveler passing through emerges at a time earlier or later than departure, according to how the clocks were desynchronized. The path through the tunnel remains subliminal locally, so causality looks intact at each step, even while the global story jumps. Engineering hurdles tower over the idea. A macroscopic stable throat requires concentrations of exotic energy beyond current laboratory reach. Quantum back reaction and instabilities may surge as soon as signals flow. Feedback might pinch the tunnel closed or create radiation storms that evaporate the structure. Even if a civilization could build one, control of synchronization, security against unauthorized edits, and treaty frameworks for temporal migration would be essential to prevent catastrophic interference between eras. Still, the concept functions as a master thought experiment. It shows that in a universe governed by geometry and energy, the difference between fast travel across space and travel across time is only a matter of how the clocks are carried. If exotic energy proves manufacturable at scale, a wormhole network would redefine distance, diplomacy, and destiny. If it does not, the constraints themselves will have taught us why time resists our hands. 5. Exact solutions of general relativity contain closed time like curves. General relativity is generous in its catalog of possible worlds. Among the exact solutions to Einstein equations are spacetimes where a traveler can follow a path that is always time-like and yet returns to an earlier event. These closed time-like curves arise in rotating universes, in certain cosmic string arrangements, and in special configurations of matter and motion. The traveler never breaks the local speed limit and never becomes light-like. Time is bent by geometry alone. Not all such solutions are physically reasonable. Some demand perfect symmetry or matter distributions that are unstable under small perturbations. Others require infinite cylinders or idealized boundary conditions no galaxy could ever provide. The contemporary view, therefore, treats closed time like curves, as warnings about the limits of classical theory rather than blueprints. Quantizing gravity or enforcing energy conditions may excise many of these curves from the list of permitted realities, yet the lesson endures. Nothing in the base mathematics prohibits time from curling if the right stresses and motions accumulate. That keeps the question open at a deeper level. Are we protected by a principle not yet derived that bans these structures in all consistent quantum theories? Or are we protected only by the difficulty of arranging the universe into the rare states that admit them? The future of theory will decide whether the prohibition is logical or logistical. Practical implications are subtle. Even if nature never forms a large-scale closed curve, small scales near extreme objects might flirt with the same geometry. Signals could experience unusual orderings. Quantum processes could amplify or damp paths that nearly close. Observations of high-energy astrophysical systems become tests of how close reality comes to the border and how it turns away. 6. The arrow of time may emerge from entropy rather than fundamental law. Microscopic laws appear symmetric when time is reversed while daily life is not. Cups shatter, but shards assemble only under careful hands. The mismatch is explained by entropy, which counts the number of microstates compatible with a macro state. Low entropy states are rare, while high entropy states are common. The universe began in a state of astonishingly low entropy, which set the arrow by biasing evolution toward more probable configurations. If the arrow is statistical rather than absolute, then pockets of reversed behavior are possible in principle. Tiny systems under careful control can be driven to run steps backward for a while. Fluctuation theorems quantify how likely such events are and show that the price is paid in information and work. Information processing becomes entangled with thermodynamics, so that measurement, erasure, and feedback decide which way the arrow points locally. This raises a radical possibility. A machine that uses information to steer microstates could lower entropy in a region and partially reverse the local arrow for short durations without violating global laws. Biological systems already exploit information to create order against noise through metabolism and repair. Technology can sharpen this edge by building feedback at molecular scales. The dream of a time switch rests on using knowledge as fuel rather than heat or momentum. Cosmic consequences follow. If the only reason time has a direction is the special beginning, then another universe born from different initial conditions might host very different temporal experience. Multiverse scenarios acquire a new richness where arrows point in patterns rather than uniformly. Our ability to travel through time may be limited not by dynamics, but by a historical accident in the first moments. 7. Microscopic entropy reversals hint at controllable local temporal flow. Experiments with single molecules and trapped particles have demonstrated transient episodes where heat flows from cold to hot, or where a process spontaneously reverses direction. These events do not break the second law when analyzed across the full distribution of outcomes. Instead, they showcase that rare microhistories can buck the average. Theory bundles these observations into fluctuation theorems that precisely predict the odds of observing negative entropy production over a finite number of steps. Control transforms curiosity into engineering. By measuring the system and applying feedback conditioned on that information, one can bias trajectories toward the rare reversed paths. The cost is paid in the bookkeeping of information. Recording, storing, and erasing bits. Add entropy elsewhere so the global ledger remains positive. Locally, though, the experimenter experiences a temporary rollback in the natural drift, which is effectively a small move against the arrow of time. Scaling this into a device would require exquisitely fast measurement, ultra-low noise, and actuators that operate on the timescales of the fluctuations themselves. Quantum devices, such as superconducting qubits or cold atoms, already sit near these thresholds. In such regimes, The boundary between thermodynamics and information theory blurs. That boundary is exactly where time becomes malleable, in the limited but tangible sense of sequence control and delay. The philosophical shift matters. Time travel may not begin as a grand tunnel through centuries, but as a laboratory knob that stretches or compresses the order of microscopic events. Industries that rely on precision chemistry, quantum sensing, or single photon technologies would be the first to exploit this. Once sequence control becomes routine at the base layer of matter, larger emergent structures will follow. 8. Quantum retrocausality models allow future measurements to influence past states. Standard quantum mechanics updates a system's description when a measurement occurs. Retrocausal models propose that boundary conditions in the future also play a role by allowing influences that run from later to earlier times inside the formalism. The goal is to explain puzzling correlations without invoking faster-than-light influence. Causes and effects thread both directions along the timeline, while signals that could be exploited remain constrained by no signaling rules. These models reframe famous experiments. In a delayed choice setup, the decision to insert or remove an interferometer element appears to determine whether a photon behaved as a wave or as a particle in the past. Retrocausal interpretations avoid paradox by stating that the photon's full story includes influences from the choice made after its emission. The description becomes global rather than stepwise, which restores consistency at the price of an unfamiliar worldview. Empirical tests are challenging. Most predictions overlap with standard quantum theory, so discriminating experiments must be crafted with care. Proposals often look for subtle statistical differences in weak measurements, post-selected ensembles, or correlations conditioned on future settings. A positive signal would indicate that the universe computes histories using constraints from both ends, rather than just from initial conditions. If supported, retrocausality would not hand over a message to the past. Constraints appear in aggregate and not as a telephone line. The deep impact would be on understanding. Time would cease to be a one-way input to dynamics and would become a two-sided boundary. That shift could unlock new algorithms for quantum control and new ways to reconcile gravity with quantum theory. 9. Delayed choice experiments challenge the idea that the past is fixed. A photon emitted long before a decision is made still behaves as though it knew that later decision. Remove an element, and the record indicates particle-like behavior. Insert it, and an interference pattern appears. The timing is arranged so that no signal traveling at or below light speed could inform the photon of the choice. The past record, therefore, depends on a future action in a way that leaves classical intuition behind. This need not imply messaging to the past. The experiment can be modeled so that the full configuration across the entire apparatus and timeline determines the outcome in one consistent stroke. The past is not literally rewritten, but rather not fully decided until the global boundary conditions are set. The clash is with the human habit of building stories step by step, where earlier chapters are locked before later ones are written. Technically, advances in single photon sources, ultra-fast switches, and long-distance interferometry have made the once abstract discussion painfully real. Quantum eraser versions extend the theme by allowing witch path information to be erased after detection while still recovering fringes in correlated subsets. Each refinement tightens the conceptual vice. Either reality carries non-classical correlations that use the whole experiment at once, or reality permits some form of influence that defies naive time order. The consequence for time travel discourse is caution and hope. Caution, because intuition about fixed pasts is a poor guide in quantum contexts. Hope, because the experiments show that nature tolerates dependencies that traditional causality would not expect. A theory that harnesses these dependencies without opening paradoxical channels could be a seed for controlled temporal technology. 10. Entanglement. Correlations appear to ignore classical time order. Entangled particles share a joint state that cannot be factored into independent pieces. Measure one and predictions about the other snap into high confidence, regardless of distance. Timing the measurements does not change the correlations. Whether one is measured first or second or nearly simultaneously, the statistics remain the same. The experiments violate inequalities that any local realist model would satisfy, and they do so while forbidding usable signaling. This is the delicate balance that preserves the world from paradox. Correlations are strong, yet they carry no message because the outcomes at each site are individually random. Only by later comparing notes do the patterns reveal themselves. The world, therefore, allows a wide web of connections that slice across time and space while keeping the channel for manipulation closed. The door looks unlocked from far away, but a hand at the knob finds it sealed. Practical applications turn this strange handicap into strength. Quantum key distribution produces shared secrets whose security rests on the impossibility of copying unknown states. Distributed sensing promises to beat classical limits by using entanglement as a resource. These technologies already stress the infrastructure of timekeeping because synchronization is central to their performance. Paradox is not required to improve the world. The lesson for temporal ambition is discipline. Entanglement rewires expectations about order, yet it does not grant license to rewrite history. Any future scheme for temporal communication would need to bypass the randomness that walls off signaling while preserving the iron constraints that experiments keep confirming. The search is not for loopholes, but for principles that guide what forms of coordination nature does allow. 11. Time crystals show order that repeats in time rather than in space. Ordinary crystals repeat a pattern in space. Time crystals repeat a pattern in time. Under periodic driving, certain quantum systems settle into a response that oscillates with a period that is a multiple of the drive rather than equal to it. The system locks into a rhythm that resists small disturbances and displays long-lived coherence. This is a form of order that lives not in location, but in timing. These phases are not perpetual motion machines because they are open systems supplied by an external drive, and they respect conservation laws. What makes them striking is the emergence of rigidity in the time domain. Correlations persist across many cycles as if the system had a backbone made of moments. That backbone can serve as a reference frame for timing operations and as a memory that stores phase relationships rather than positions. Engineering prospects include ultra-stable clocks, robust qubits, and sensors that survive environmental noise by encoding information into temporal patterns. The concept expands the palette for designing materials. Instead of drawing lattices in space, one draws schedules of response in time. The design language becomes choreography as much as geometry. For time travel dreams, the relevance is subtle but real. If order can crystallize in time, then the assumption that time is a smooth parameter begins to wobble. Discrete beats and subharmonic locking hint that the fabric of evolution can support structures built from repeated patterns. Those structures might one day anchor devices that stretch or fold the local experience of duration without relying on massive gravity. 12. Planck time may be the smallest operational tick of reality. Combine fundamental constants, and a natural unit of time emerges that is unimaginably small. This Planck time is the duration light needs to cross a Planck length, and it sets a scale where quantum effects of gravity refuse to be ignored. Below this scale, the notions of continuity and smooth evolution become suspect. The usual calculus of change might give way to a rulebook written in discrete increments. If a smallest tick exists, then dynamics become a sequence of updates rather than a flow. That has consequences for causality, because contiguous cause and effect assume a continuous medium. Discreteness introduces a new kind of grain that software engineers understand well. Sampling rates, aliasing, and synchronization become physical issues, not just engineering choices. Signals cannot carry more than 1 bit per tick, and interference patterns may encode the hidden clock. Searching for the tick requires clever experiments. Observations of gamma-ray bursts have been used to test whether high-energy photons disperse in ways that betray granular space-time. Interferometers attempt to detect correlated jitter that would arise from a fundamental noise floor. So far, the results are consistent with smoothness, which pushes any discreteness deeper or refines how it hides. A confirmed tick would not immediately hand over travel through time. It would, however, reshape strategies. Devices might latch onto the master cadence to skip states or to insert delays at the base layer of evolution. The constraint of a smallest tick could become the lever by which tomorrow's engineers pry time free from the continuum. 13. Space-time foam at the Planck scale could scatter time itself. At scales far smaller than atoms, the metric of space-time may fluctuate violently. Quantum uncertainty would then turn the smooth manifold into a froth of transient curvature. Paths that look straight on large scales would wobble at tiny scales. Light cones that define what can affect what would blur at their edges. The clean diagram used in classrooms would be a coarse average of an unruly substrate. This foam would add noise to timing. Photons traveling from distant explosions might arrive with minute spreads that depend on energy. Interferometers might see phase wander that cannot be eliminated by better mirrors or colder temperatures. The noise would not be ordinary vibration, but a new category of jitter authored by reality itself. Detecting such jitter would confirm that time is not merely bent by mass, but is intrinsically restless. Technological consequences are double-edged. On one hand, irreducible noise sets a hard floor on precision, which limits clock stability and navigation accuracy. On the other hand, structure in the noise could be harvested as a signature. Instruments could read the foam to learn about quantum gravity, the way seismographs read the crust to learn about Earth. A new science would bloom, whose data is carried by the way time scatters. For travel across time, the foam would act as weather. Routes that depend on phase coherence or delicate interference might fail when the substrate whips and churns. Routes that anchor in robust geometric features would fare better. The first-time pilots would therefore be part physicist and part navigator, reading a temporal sea that never entirely calms. 14. Chronon-based theories propose that time is built from discrete units. A chronon is a hypothetical quantum of time. Instead of a real line of instants, there would be a ladder of steps. Dynamics would proceed by hops from one rung to the next. Energy, momentum, and other quantities would inherit constraints from that step size. The idea has appeared in multiple frameworks as researchers search for ways to unify quantum theory with gravity without infinities. Discrete time would regulate divergences in calculations by eliminating arbitrarily short intervals. It would also force a revision of symmetry principles that assume continuous translation. Conservation laws might acquire corrections that become visible at high energies or over cosmological spans. These corrections could be measured by clock networks, particle experiments, or astronomical observations if their fingerprints are strong enough. Skepticism is healthy because many elegant discrete models reproduce known physics only approximately, or only in special regimes. Bridging from a tidy lattice picture back to the continuous experience of daily life requires care. The passage from discrete to continuous must recover the equations that work so well for engineering and astronomy. Any mismatch becomes an opportunity to falsify the hypothesis. If discrete time survives these tests, it equips engineers with a new kind of control surface. One could imagine devices that skip rungs or that lock phases to specific congruences, the way modern electronics lock to reference clocks. Temporal aliasing could be sculpted into functions. The crude dream of a time button becomes a refined practice of time coding. 15. Tachyon ideas test the possibility of faster-than-light temporal messengers. Tachyons are hypothetical particles that always move faster than light. In the mathematics of special relativity, such motion flips the order of events between different observers. A message carried by a tachyon could be received before it was sent in some reference frames. The concept therefore becomes a stress test for causality. If tachyons exist in any usable form, then time order would be up for renegotiation. The obstacles are severe. Faster-than-light modes tend to destabilize quantum fields by letting energy run downhill without limit. Interactions would generate runaway production of tachyon pairs which would quickly wreck the vacuum. Careful theoretical work often reinterprets apparent tachyonic signals as markers of instability that resolve into ordinary particles after the system relaxes to a lower energy state. The hope of a persistent superluminal courier fades under such reinterpretations. Experiments have hunted for signatures in cosmic rays, collider data, and neutrino timing. Claims that neutrinos outran light dissolved when systematic errors were corrected and cables were checked. The repeated pattern is instructive. Nature keeps granting counterintuitive effects, yet it shields causality from direct assault. The lesson is that the constant speed of light is more than an engineering nuisance. It is a scaffold for a consistent world. If tachyons never appear, the void they leave is useful. It tells designers to stop chasing raw speed through space-time and to pivot toward geometry and information. Instead of outrunning light, one shapes the path so that less time accumulates or one exploits correlations that bind outcomes without carrying signals. The horizon for progress moves from the racetrack to the blueprint. 16. Frame dragging near a spinning singularity distorts the sequencing of events. A rapidly rotating compact object pulls the surrounding spacetime into a whirlpool so that nearby motion is forced to co-rotate. This twisting becomes extreme in the ergosphere, where the local definition of standing still breaks down and every possible trajectory acquires a compulsory spin. Clocks that try to keep impartial time inside such a region accumulate seconds at rates that depend on direction and proximity, which means event order becomes path-dependent in a way unknown to everyday experience. Instruments designed to timestamp signals would disagree not because of malfunction, but because time itself is being sheared by rotation. Engineering a probe for this environment demands navigation that anticipates geometry rather than forcing through it with brute thrust. Course planning must account for how orbits precess and how small changes in angle snowball into large changes in elapsed time. Communication links will require predictive synchronization, since the return of a signal cannot be assumed to mirror the outbound leg. Even power budgets are affected, because frame dragging can donate or absorb energy from passing craft depending on alignment, which in turn changes the schedule of onboard systems that depend on precise timing. The physics invites experimentation. Gyroscopes that float in highly stable trajectories could map the twist directly through the drift of their axes. Interferometers that compare light paths grazing the ergosphere would reveal phase shifts that no Newtonian model can explain. Polarized radiation from accretion flows carries a fossil imprint of the rotation pattern, and the time order of flares would act as a stopwatch written in plasma. All of these measurements make time a local property, sculpted by motion, rather than a universal background. If time can be sheared, it can be budgeted. A civilization that lives near a fast spinner could schedule tasks to run where the geometry grants them longer subjective duration, while exterior calendars sprint ahead. Research programs that require patient iteration would retreat into these eddies, while long-term watchers outside monitor decades of political or economic change. The device is not a tunnel to yesterday, yet it is a tool that pries personal history free from the global page count. 17. Gravitational redshift can be harvested as a practical clock for time travel experiments. Light that climbs out of a gravitational well loses energy, which shows up as a shift to longer wavelengths. The same principle explains why a clock deeper in the well ticks more slowly than one higher up. By arranging a ladder of clocks from basement to rooftop and comparing their readings with optical links, one can watch gravity tug on time in real laboratories rather than only in thought. These comparisons are already so precise that moving a clock by the height of a desk can be detected as a change in tick rate. Turning this into a tool for temporal engineering begins with metrology. A local map of gravitational potential becomes a map of how time flows, which means surveys for tunnels, dense ore bodies, and underground voids can be conducted with timing rather than shovels. Networks of optical lattice clocks tied by fiber or satellite can watch tides, groundwater, and even traffic as ripples in the field that modulate seconds. Once the world is seen as a landscape of faster and slower time, the next step is to exploit the gradient. Experiments can place quantum systems at two heights simultaneously through interferometry with cold atoms. The phase difference becomes a record of the time each path experienced, which is gravity, turned into a ruler for temporal contrast. Materials and chemical reactions can be tested to see how rate-dependent phenomena behave when one sample ages faster than a twin. Computation that depends on clock edges can be distributed across the gradient to test whether timing asymmetry yields any advantage for algorithms that tolerate skew. These are modest maneuvers when compared with cinematic machines, yet they are authentic and repeatable. They establish the habit of thinking about time as a resource that can be moved around at will by shifting altitude or mass. With enough precision, the same habit scales upward to orbits around compact objects, where the contrast grows to life-changing proportions. The future of time travel starts here with a stack of clocks and the patience to compare them. 18. A spaceship that accelerates hard enough can leap decades into a planetary future. Relativistic kinematics rewards travelers who can sustain strong acceleration, with dramatic differences between ship time and home time. A craft that provides artificial gravity through constant push would allow the crew to live in comfort while velocity climbs toward a significant fraction of light. Turnaround at the midpoint flips the push to braking so that the crew walks on the same deck in the same direction for the entire voyage. When they return, their personal calendar shows only a handful of years, while the origin world has spun through decades. The barriers are practical and severe. Energy must be furnished at an industrial scale that dwarfs contemporary grids, and must be delivered in forms compatible with mass fractions that leave room for payload. Heat must be rejected relentlessly because waste energy cannot be allowed to accumulate inside the hull. Interstellar particles hitting the bow at relativistic speed become radiation and sandblasting at once, which implies magnetic shielding, sacrificial forward mass, and perhaps self-healing fields that deflect and repair on the fly. Human performance sets additional limits. Even with comfortable acceleration, a crew must sustain mental health during isolation and must negotiate the shock of cultural discontinuity upon return. Medicine develops on different tracks for the travelers and for those who remain planet-bound, which complicates care. Law will follow with questions about jurisdiction over people whose passports were issued by institutions that no longer exist or whose obligations have aged without them. The personal drama of the twin narrative becomes the basis for policy. The payoff most relevant to time is experiential. A person can aim themselves at the far future within their own lifetime without needing cryogenic suspension or biological redesign. They would become a messenger from the past by living forward at a slower rate and returning with knowledge of a world that has moved on. There is no paradox, only the courage to step onto a different slope of the same space-time. 19. The twin scenario proves biological aging can be stretched by speed. When one twin stays home and the other departs on a high-speed journey, the symmetry is broken by acceleration. The traveling twin experiences fewer heartbeats and fewer biochemical cycles for the same span of home time. The effect is not a trick of measurement, but a mismatch in how much proper time accumulates along two different world lines. Particle laboratories have stretched the lifetime of unstable particles with velocity, and global navigation has corrected for tiny discrepancies in satellite clocks for years, which means biology sits inside this web of timing whether we notice or not. Stretching aging demands careful thinking about what counts as time for a living system. Cells divide on schedules that depend on temperature, nutrients, and gene regulation. Proteins fold and unfold in cycles, and neurons fire in rhythms that generate memory. All of these processes depend on the same physical seconds as the orbiting clock, yet they can be modulated by environment in ways that confuse intuition. A traveler who lives more slowly than their peers might still suffer damage from radiation or stress that ages them in other senses, which means time stretching is not a universal shield. The experimenter faces ethics. Trials with animals or volunteers in long-duration, high-speed scenarios are not coming soon. Instead, the evidence will remain indirect through precise timing of biochemical reactions in moving frames and through models that integrate physiology with relativity. Spaceflight provides a bridge because astronauts already show changes in telomere dynamics, bone density, and circadian rhythms that inform how living systems adapt when the background of time differs from Earth norms. When the method matures, people will begin to plan life in world-line strategies, rather than only in careers and addresses. Scholars might choose a slow path to harvest a longer, productive window, while artists might prefer to age with audiences in the shared calendar. Those who choose to leap ahead will not look younger than those they left behind, because beauty and vigor are more than tick counts. They will, however, carry the deep feeling that their biography was stretched, and that feeling will write new literature and new law. 20. Event horizons redefine before and after for infalling observers. An event horizon is not a wall in space, but a boundary in the book of events. For a person who falls through one, nothing special must occur locally if the black hole is large enough to keep tides gentle at the border. For a person who stays outside, no signal from the infaller ever returns after the crossing, and the image appears to fade and redshift rather than to disappear. This split creates two valid stories about the order of moments that refuse to be spliced into one universal tale. Inside the horizon, light cones tip so that every path forward leads deeper. The meaning of before and after becomes tightly centered on the traveler and loses connection to the outside narrative. Clocks can be carried and equations can be solved, yet the power to compare notes with distant observers is gone, which means arguments about what really happened become arguments about which world line a person cares to privilege. Physics tolerates both because the geometry admits both, and because no contradiction can be exported from one side to the other. For technology, this boundary is an invitation to design instruments that tell two different kinds of truth at once. External telescopes can read polarized light from plasma near the edge to reconstruct the dance of fields and matter, while internal probes can report what a coherent system experiences as it drifts toward regions of extreme curvature. The reports will never be reconciled into a single movie, which is not a failure, but a lesson about how time is local and context-bound. Time travel discourse gains humility from this. The most dramatic boundary in the universe already proves that there is no master sequence of events suitable for all observers. If the goal is to move between eras, then the first step is to accept that the definition of an era itself depends on where one stands and on which channels remain open for comparison. 21. Wormhole mouths moved at different speeds could desynchronize their clocks. A wormhole that connects two mouths inherits the histories of those mouths. If one mouth spends time in a fast-moving vehicle while the other rests, their internal clocks will disagree upon reunion. A traveler who enters through the stationary mouth and exits the moved mouth would step into a time that is offset relative to the entry. The apparent jump arises without any segment of the journey violating local causality, since each leg respects the speed limit, and each clock does nothing more exotic than tick at its experienced rate. The subtleties begin with stability. Any attempt to transport matter through a maintained throat must account for how energy conditions are being skirted by negative energy density, and how quantum fluctuations threaten to slam the passage shut. A traffic plan must limit throughput to avoid building up stresses that trigger instabilities. The act of moving a mouth can also pump energy into the geometry in ways that create dangerous feedback, unless the acceleration profile is smooth and the environment is free of strong radiation fields. Security is a second layer. A device that allows a jump in time is also a device that can be abused to escape accountability or to collapse markets by realizing information earlier than fair. Governance would need to include cryptographic proof of entry and exit events, notarization of transfers, and shared oversight that prevents any single actor from unilaterally altering the offset. The infrastructure would resemble a central bank for seconds, with audits that track temporal debt as carefully as financial debt. Even if such prudence is achieved, society will learn quickly that offsets do not grant omnipotence. You cannot send a message to a time before the offset was established because the mouths share a common origin that anchors their earliest possible exchange. You cannot build infinite loops of advantage because the device is bounded by how much desynchronization its history can support. What the device does grant is surgical displacement, which is enough to rewrite logistics and to challenge notions of fairness. 22. Exotic negative energy density is the price of keeping a wormhole open. Gravity pulls inward on everything that carries positive energy, which means a tunnel made of ordinary matter collapses before a traveler can cross. The equations allow the opposite sign energy in small doses and special arrangements which generate pressure that pushes outward against the squeeze. Quantum fields can produce negative energy in squeezed states and between plates that restrict modes, so in principle, the sign is not forbidden. The catch is that the amount and duration appear to be tightly limited by rules that prevent exploitation. Building a macroscopic structure requires threading a loophole through these rules. A designer would attempt to scaffold a throat with regions of negative energy that are renewed as they decay, so that the tunnel remains traversable. Distributed control would monitor stresses and route traffic to avoid hotspots that invite collapse. Materials must endure incredible gradients while staying transparent to the fields that deliver the exotic pressure. The architecture looks less like a bridge and more like a constantly tuned instrument. Laboratory work at small scales shows that negative energy is real but fragile. Casimir setups measure forces that demonstrate the sign change yet scale for only microscopic gaps. Optical tricks can squeeze light to produce local dips below the vacuum baseline, yet those dips are compensated by spikes elsewhere that restore balance over time. Each success reads like a telegram from the quantum world that says the door is there, but it is narrow and guarded. If the price is too high, the lesson still pays. The same techniques that try to stabilize a throat can be redirected into sensors that read tiny distortions in space-time or into communication systems that encode information in vacuum fluctuations. The quest for grand travel through tunnels may end in a family of humble tools that translate the fine print of quantum fields into devices that stretch how we use time without tearing the fabric. 23. Quantum inequalities set limits on how much negative energy can exist. The quantum field does not allow a free banquet of negative energy. Theorems derived from the structure of the vacuum state show that any region with a deficit must be compensated by surpluses nearby, and that the size and longevity of the deficit cannot exceed bounds that scale with the observation time and the sampling function. This is the accountant that stands at the threshold of every exotic proposal and tallies what is permitted before instability or causality trouble erupts. For engineering minds, these inequalities behave like design codes, a blueprint that demands a throat with a certain radius, and dwell time must be checked against the permitted budget. If the numbers fail, the plan is not merely difficult, but forbidden by first principles. Workarounds include distributing the load, pulsing the fields so that no single area violates the bound, or moving the entire device along a trajectory that shares the stress across time rather than across space. Measurement offers another path. Even if one cannot break the bank, experiments that approach the limit teach us where the border lies. Precision interferometry Superconducting circuits and photonic structures can be tuned to press against the inequalities and to record how the vacuum responds. The outcome is a map of what is possible, which converts speculation into a catalog of permitted tricks. Designers can then combine the tricks into composite systems that accomplish surprise outcomes while respecting every line of the ledger. The cultural value is clarity. A community that understands why some dreams fail gains focus for the dreams that remain. Time travel fantasies often dissolve into paradox when scrutinized, yet the residue is a set of tools that tighten clocks, stabilize qubits, and sharpen sensors. Limits are not the end of ambition. They are the rails that allow the train to move fast without disaster. 24. Cosmic strings may bend time into almost complete loops. A cosmic string is a hypothetical filament of energy so dense that space around it forms a cone with a deficit angle. Two strings that pass by each other at high speed can create a geometry where a path around them returns closer to its starting time than should be possible. Push the parameters hard enough in the equations, and closed time-like curves appear, which lures the imagination toward machines made of primordial defects instead of metal. Whether such strings exist is an open question that radio surveys and gravitational wave searches continue to address. The signatures to watch are bursts from cusps on loops, distinctive lensing patterns that split background galaxies with sharp edges, and a low hum of gravitational waves that would build a frequency spectrum unlike that of ordinary binary systems. Any confirmed detection would immediately shift the time travel discussion from pure speculation toward a hunt for configurations that maximize temporal curvature without catastrophic side effects. The challenges are sobering. Strings would be dangerous neighbors because their energy density would tear through ordinary matter, and their motion could emit radiation at levels that threaten planets. Containment would be a grand task, and steering them into controlled encounters would require forces far beyond current technology. Even if all of that were solved, the near loop achieved in realistic scenarios might still fall short of a complete closure, which means one gains pronounced time dilation and odd sequencing, but not a clean return to an earlier event. In practice, then, the best service strings might render is as cosmic laboratories. They would be natural places where the universe itself constructs extreme spacetimes that test every idea about causality, quantum fields, and geometry. A science that learns to read the timing around strings would be a science trained to respect the wildness of the fabric and to use that respect to design gentler instruments that still get the job done. 25. Tipler cylinder concepts explore rotation as a route to temporal return. Mathematics shows that an infinitely long, extremely dense cylinder spinning fast enough would drag space-time into helical paths that allow closed time-like travel around it. The construction is implausible in its pure form, because real matter resists the required density, and because nothing is infinite. Variants suggest finite but very long cylinders or arrays of masses that imitate the effect for limited regions. The attraction is that only ordinary matter and motion are invoked rather than exotic energy. The physics of materials quickly intervenes. Stress from rotation would exceed tensile strengths by many orders, and friction would pump waste heat into the structure until it destroys itself. Magnetic levitation or superconducting tricks can reduce bearings, but not remove the fundamental need to keep the mass coherent at absurd angular speeds. The surrounding environment would also be flooded with radiation and gravitational waves as the device shakes space-time with each tiny imperfection. Despite those walls, the idea remains educational. It proves that geometry can, in principle, be driven by rotation into regimes where time order becomes circular. It motivates smaller experiments where rotating fluids, superconductor rings, or ring lasers reveal frame dragging on gentle scales. Precision gyroscopes have already measured the tiny twist produced by Earth, which confirms that the mechanism is real, even if the grand device is not. The final value of the cylinder is as a compass needle. It points toward rotation as a handle on time and invites the community to look for other handles that are less punishing to matter. When time finally yields to engineering, it will likely be through a family of subtle handles rather than through one impossible machine. 26. The second law of thermodynamics might be local rather than universal. The law that entropy increases is the most reliable trend in daily life, yet it is framed as a statistical statement that applies to closed systems. The universe is not obviously closed at scales that matter to biology and technology, and many processes exchange energy and information with surroundings in ways that change the accounting. Local decreases in entropy are common whenever work is applied and whenever feedback uses knowledge to steer outcomes away from chance. If the law is local, then the arrow of time is a property that can be redirected by building the right boundaries. Refrigerators push heat uphill by paying an electric bill. Error-correcting codes push noise out of data streams by carrying redundancy that is paid for with bandwidth. Biological repair pushes cells back toward order by metabolizing chemical fuel. Each case obeys the law globally, even as it violates the naive expectation locally, which is the clue that design can carve pockets of reverse drift. The strategy for temporal engineering follows the same template. Choose a subsystem, feed it energy and information, and allow the surroundings to absorb the compensating cost. Within the pocket, sequences can be rewound or at least slowed enough to offer a sense of rollback. Chemical reactions can be coerced to unmix where they would normally mix. Microscopic machines can ratchet motion against thermal agitation. None of this sends a person to yesterday, but it is a beginning in which sequence is no longer sacred. The broader philosophy becomes one of choreography. Build boundaries that define a stage, then compose flows of energy and information that make the stage run a script different from the street outside. The skill would be as much artistic as mathematical, because the goal is to shape impressions of order over time, without ever lying to the global bookkeeper that counts entropy in the wings. 27. If entropy is statistical, rare decreases could permit micro-time slips. Probability allows the improbable on a long enough timeline, which means any finite system will occasionally run backward a step under the right conditions. In a gas, this looks like a cluster of molecules spontaneously moving from spread to clump for a brief moment. In electronic noise, it looks like fluctuations that mimic a coherent signal for a breath before dissolving back into randomness. The odds scale poorly with size and duration, so macroscopic reversals are effectively absent, yet microscopic reversals are real and can be caught with fast sensors. A micro-time slip can be turned into a tool when feedback trapping is added. A controller watches for the start of a reversal and then locks in with a pulse that holds the system near the reversed state longer than chance would allow. The pulse must be applied with exquisite timing so that the controller nudges rather than overwhelms. In effect, the world supplies a free seed of order, and the experimenter waters it before it wilts. Repetition trains the system to visit reverse paths often enough to matter. The harvest is not science fiction. Single-electron devices that operate near the thermal limit already flirt with regimes where erasure and writing costs ride directly on fluctuation theorems. Colloidal particles in optical traps can be coaxed to run work cycles that appear to defy the arrow until the accounting for information closes the loop. Quantum bits can be post-selected to reconstruct unlikely trajectories that tell a story in which the tail wags the dog for a few frames. What emerges is a philosophy of micro-patience. Rather than punching a hole through time, one listens for moments when time rustles and one slides a wedge into the crack. The result is measured in nanoseconds, not years, yet revolutions in computing, chemistry, and sensing are built from mastery over tiny intervals. A world full of micro-slips would feel different because the timing of events would be an instrument rather than a fact. 28. Information theory links the arrow of time to the growth of knowledge. Entropy was reimagined in terms of missing information about microstates, which ties the thermodynamic arrow to how knowledge evolves. When an observer acquires data and stores it in memory, their local entropy can decrease because uncertainty falls. The cost is that somewhere else energy is spent, and waste heat rises, which preserves the global direction. This balance explains why measurement has a thermodynamic bill and why erasing memory is heated work rather than a neutral reset. In practice, this means that sensors, computers, and minds are machines that trade energy for order in the temporal sequence of their internal states. A predictive model that successfully forecasts the next moment turns chaos into structure and wins time in the sense of reduced surprise. Error correction extends memories across longer intervals by actively pushing back against the forgetting that noise would impose. The arrow becomes something we shepherd rather than something that sweeps us along. Strategies that maximize useful knowledge per unit of energy will therefore feel like time technologies, even if they never bend a geodesic. A habitat that learns its users to preheat only when needed reduces thermal noise in the daily routine. A spacecraft that infers micrometeoroid flux from tiny vibrations schedules protective maneuvers in advance and changes the order of impacts in practice by not being where chance predicted. These are small edits to sequence achieved through knowledge. At the philosophical limit, free will looks like the system-level ability to write sequences that would have been improbable without the computation that generated them. A future that is shaped by predictive models and by memories held against noise is a future in which the arrow of time is braided with the arrow of learning. Those who master the braid will feel as though they have tamed duration itself. 29. The block universe view treats past, present, and future as equally real. One interpretation of relativity treats the entire space-time as a four-dimensional object where every event simply exists. In this view, the sensation of a moving present is an emergent feature of how brains process information and of how entropy structures records rather than an objective flow. Traveling through time becomes ambiguous in such a picture because every destination is already there and every journey is a path within a fixed sculpture rather than a traversal of a changing river. Adopting this perspective changes questions more than answers. Instead of asking whether we can go to the past, one asks whether paths exist that connect one event to another without violating local physics. The focus shifts from altering what is to locating where we are inside what is. Many puzzles soften because paradox becomes a misuse of language rather than a violation of law. You cannot change an event in a block because change presumes a sequence outside the block. Critics argue that this view drains meaning from agency and from moral responsibility. If everything is written, choice looks like theater. Defenders answer that the writing includes the choosing, and that agency is a pattern inside the block that evaluates options and acts accordingly. The debate is not settled, but it has practical consequence for how people approach engineering grand projects. A block view encourages designs that aim to find allowed paths rather than to force forbidden ones. For a creator of time technologies, the block universe is a stern mentor. It suggests that the route to success is to search for geometries that already permit exotic connections and to build vehicles that can survive those routes. The goal is not to change the block. The goal is to find the threads within it that carry one to a desired page. 30. The growing block view preserves an expanding frontier of now. A different picture holds that the past is fixed and real, while the future is open and not yet part of reality. The present is the moving boundary where potential becomes history, and each new slice is added to the growing archive. This model fits human experience more closely and relieves some discomfort about agency, since choices appear to create genuine novelty. It also reframes time travel as a question about whether the boundary can be folded or whether archived pages can be re-entered. If the archive is immutable, then visiting the past would be observation without edit. You could walk through a museum of moments without any lever to rearrange exhibits. Practical value would remain because access to perfect records changes science and justice profoundly. If, however, the archive can be touched, then consistency constraints must arise to prevent contradictions. The most natural constraint is that any action taken during a visit was already part of the archived history, which preserves logical closure while making freedom a carefully curated illusion. Technologies that fit this worldview would emphasize recording at absolute fidelity. Quantum non-demolition techniques that read systems without collapsing key properties become desirable. Cosmology that treats background radiation and relic neutrinos as the fossil record of early times becomes the template for archaeology at every scale. The dream is to build instruments that reduce the growing frontier to a razor by harvesting almost all information about each new slice as it arrives. From a storytelling angle, the growing block grants a different promise than the eternal block. It says the future is genuinely plastic, and that engineering can write new chapters rather than only locate existing ones. The cost is that travel to earlier pages may be constrained to spectating or to actions that were always part of the print. The payoff is a deep motivation to design the boundary itself, so that when it sweeps forward, it leaves behind pages worth revisiting. 31. Causal set theory builds space-time from discrete order relations. In this program, space-time is not a smooth fabric, but a vast, partially ordered set whose elements are elementary events, and whose arrows encode which events can influence which. Distance and duration emerge from the density of these relations, rather than from coordinates painted onto a continuum. The geometry that we draw with curves and metrics is recovered statistically when the number of elements is enormous and the order has the right randomness. Time is literally the growth of order in this picture, and the continuum is only the blurred shadow of an underlying tally of befores and afters. This approach changes what a time machine would mean. You cannot slide continuously to an earlier coordinate because coordinates are not fundamental. You would need to add or delete order relations, which is to say, you would need to alter the causal set itself. That is a different kind of manipulation from bending a smooth manifold, and it hints that the real price of temporal engineering is paid in control over which events are permitted to be ancestors of which. The dream becomes one of editing precedents rather than of drilling tunnels. Evidence would come from subtle departures from continuum predictions at extreme precision. Fluctuations in the number of elements sprinkled into a region would create jitter in measured volumes, which in turn would appear as tiny noise in clock comparisons and interferometry. If such noise matched the distinctive statistics predicted by a random partial order, it would be an early signature that time is grainy and relational at bedrock. The promise is conceptual clarity. By making causality the primitive and geometry the consequence, the theory aligns with how experiments are recorded as chains of influence. If the world is built in this way, then practical time control will require tools that add and remove order links in a consistent way. That suggests a future laboratory where the units are arrows of influence rather than meters and seconds. 32. Emergent time ideas suggest time arises from quantum entanglement structure. In many body quantum systems, the patterns of entanglement encode which subsystems know about which others and how correlations spread. Some proposals claim that what we call time is the bookkeeping of how entanglement grows and reorganizes. In this view, a smooth temporal parameter is not fundamental, but emerges from the rearrangement of quantum information, much as temperature emerges from the agitation of molecules. The arrow then points in the same direction as the natural growth of entanglement and stalls only when correlations saturate. Such a picture reframes clocks. A good clock is then a device whose entanglement with its environment is tightly controlled so that its internal correlations advance at a stable rate. Disturb the pattern and the rate drifts. Protect the pattern and the ticks hold. This makes error correction and isolation more than engineering choices. They become acts that define what time a subsystem experiences by dictating how its information couples to the surroundings. Travel through time becomes a question of whether one can sculpt entanglement growth to emulate faster or slower temporal progress. Quantum simulators already demonstrate that changing interaction graphs can make complex systems thermalize quickly or remain many-body localized for astonishing durations. Those are experiments in entanglement pacing. A future device might use similar tricks to grant a laboratory region extra subjective duration while the outside cruises ahead without invoking gravity or high speed. If this program is right, then the ultimate levers of time are gates on quantum information rather than mass or motion. That is both sobering and empowering. It removes the romantic image of a shining tunnel and replaces it with racks of qubits and a wiring diagram. It also makes the goal feel reachable because we already manipulate entanglement daily in laboratories and data centers. 33. The thermal time hypothesis connects time flow to the state of a system. The hypothesis proposes that given a physical state and the algebra of its observables, there is a natural flow that plays the role of time, even when no external clock is specified. The generator of this flow depends on the state itself, much as temperature depends on the distribution of energy. Time becomes a property linked to what is, rather than a global stage that sits indifferent to content. Two different states lead to two different intrinsic flows. This shift solves puzzles in generally covariant theories where no preferred time parameter exists by assigning time to the system under study. It also hints at engineering possibilities. If flow is state-dependent, then by preparing special states, one could slow or hasten the intrinsic evolution of chosen subsystems. The trick would be to design states whose modular flow takes on programmable speeds or directions while remaining stable against noise. Experiments that touch this idea already exist in the control of open quantum systems, where reservoirs can be tailored to steer the effective dynamics of a device. By sculpting the environment, one adjusts the perceived passage of time inside the device because relaxation, dephasing, and thermalization become different curves. The thermal time hypothesis suggests a deeper unification of these tricks, where state and time are locked together by principle rather than by convenience. For time travel dreams, the lesson is precision. If time is a flow that belongs to a state, then the path to control is through state preparation at exquisite fidelity. The laboratory of tomorrow will not push against a cosmic river. It will brew the river it needs inside the glassware it can hold. 34. Quantum tunneling may shift events in time as well as in space. When a particle tunnels through a barrier, it appears beyond a classically forbidden region without crossing the barrier in any familiar way. The question of how long tunneling takes has sparked decades of debate and ingenious measurement strategies. Some results suggest effective traversal times that are shorter than any naive expectation, which raises the specter of temporal surprises that accompany spatial hops. Turning this into a tool would require stable control over barrier shapes and over the initial wave packets, so that statistics narrow to a usable window. Semiconductor structures already allow programmable barriers for electrons, and optical analogs allow similar control for photons. If a regime can be found where the temporal characteristics of tunneling can be steered, then devices that create controlled delays or advances in event timing would emerge at the quantum scale. Causality survives because no signal outruns light in any unambiguous sense. The statistics that look fast are arranged so that no message can be carried without the classical shadow that restores order once full data is compared. Yet within that constraint there is room to shape when detections line up and how sequences overlap. That room is enough to build instruments that stretch or compress microscopic schedules for sensing, computing, and cryptography. The practical value would arrive quietly. A detector that gates at precisely the right instant can lower noise dramatically. A logic element that synchronizes through tunneling windows can compute with fewer errors. These are time edits, measured in picoseconds, yet they accumulate into systems that behave as if they had bent time into a more cooperative posture. 35. Weak measurement techniques appear to retrieve traces from the future. A weak measurement gently probes a quantum system without collapsing it strongly, and when combined with post-selection on a later outcome, it can yield averages that look like they came from a conversation across time. The later choice of which subset to keep seems to shape the earlier weak readout in a way that defies classical storytelling. No contradiction arises because the information is statistical and requires the full record to interpret. This toolbox turns into a kind of temporal microscope. By arranging sequences of weak probes and selective keeps, one can reconstruct aspects of a system's evolution that are invisible to strong single-shot measurements. The reconstruction leans on both the past preparation and the future choice, which makes it feel as if both ends of the timeline are holding the ruler. The effect is subtle, yet repeatable, and already powers precision protocols in laboratories. Applied ambitions include error tracking in quantum processors, where weak peaks keep tabs on qubits without demolishing their coherence, and ultra-sensitive metrology, where the combination of small disturbance and smart selection amplifies tiny signals. In both cases, a future decision about which data to retain sculpts the meaning of an earlier read, which echoes the theme that time in quantum mechanics is often a joint product of boundary conditions. For temporal engineering, the lesson is humility and creativity. We do not get messages from tomorrow. We do get methods that let tomorrow's choices refine how we understand today's gentle touches. Build enough of these refinements into circuits and sensors, and the overall system begins to feel like it has learned to lean on the future without cheating. 36. Retrocausal interpretations remove paradox by letting causes run both ways. Instead of insisting that influences only move from earlier to later times, these interpretations assign boundary conditions at both ends and compute histories that satisfy both. Paradox evaporates because a would-be contradiction is simply a boundary choice that has no compatible history. The universe is not a movie played forward, but a solution to a global constraint where outcomes and preparations cooperate. Such a stance offends intuitions, trained by everyday sequences, yet it matches how mathematics treats many physical problems, where end conditions guide solutions. It also aligns with the character of quantum correlations that seem to link distant events without usable signals. Influence in both directions preserves consistency while refusing to open a channel for communication that would explode causality. Testing these interpretations requires experiments that can discriminate them from standard readings. Proposals focus on carefully arranged choices that reveal tiny differences in statistics for weak or post-selected measurements. Even if the differences remain elusive, the conceptual payoff is significant because it teaches engineers to think in terms of global designs rather than stepwise plans. The shape of the entire apparatus across time becomes the real machine. If temporal travel ever becomes practical, it will likely exploit this design philosophy. One will not hammer a path into the past. One will build structures whose whole story across time admits the desired connection while denying paradox. The craft becomes writing boundary conditions that make a bridge inevitable. 37. Superdeterminism challenges the freedom of experimental settings. This interpretation argues that the choices experimenters make about settings are not independent of the hidden variables that determine outcomes. The correlations that violate classical expectations then do not demand non-local influence because the common cause already encoded the match between knob choices and particle properties. The price is giving up the comforting idea that settings can be selected freely of the system under test. If taken seriously, this view pushes temporal questions into the structure of initial conditions. The world is choreographed so that apparent surprises are prearranged. That does not mean laboratory work is pointless. It means the role of experiment is to uncover the choreography rather than to poke a system into new dances. Time travel looks different here, because any journey must have been part of the choreography from the outset. Critics warn that this route risks immunizing a theory against falsification by attributing every inconvenient correlation to predetermined conspiracy. Defenders counter that models can still be precise and predictive while embedding the dependencies, and that the reward is a fully local picture. The debate continues in the literature and in the design of experiments that try to push independence to cosmic scales by choosing settings from distant astronomical sources. For an engineer, the moral is about assumptions. Many grand designs fail not because of physics, but because hidden dependencies were ignored. Superdeterminism, whether right or wrong about nature, teaches builders to hunt relentlessly for unnoticed couplings that turn free choices into correlated traps. Time control will not forgive sloppy thinking about independence. 38. The no-signaling principle may protect causality while allowing strange correlations. Across every demonstration of quantum weirdness, a consistent fact holds. No observer can use entanglement or similar effects to send a message faster than light or backward in time. The marginal statistics at each station remain stubbornly random until records are compared by ordinary communication. This principle is not an extra rule tacked on after the fact. It is woven into the mathematics in ways that prevent information from being extracted from correlations at a single location. The result is a world that feels conspiratorial. Patterns exist that defy classical explanation, yet they steadfastly refuse to become channels for control. For time travel discussions, this is both a wall and a safety rail. It blocks the simplest schemes for messaging the past, while permitting architectures that use correlations to coordinate actions once future comparison becomes possible. Engineers have learned to turn the wall into a feature. Quantum key distribution uses the impossibility of copying unknown states to detect eavesdropping. Distributed sensing ties separated instruments together with shared entanglement that beats classical performance once data is merged. In each case, no single site gains an unfair preview, yet the group wins after synchronizing across normal time. The principle, therefore, sketches an allowed zone for temporal technologies. Build devices that respect no signaling locally, but harvest advantage globally, and you stay inside the lines that nature draws. Outside those lines, claims tend to collapse when cables are checked and clocks are calibrated. Now, can you write me an effective introductory paragraph? Have a lot of suspense, hold the audience, make a promise. Avoid cliches. 39. Quantum teleportation moves information through entanglement without crossing time. Teleportation does not move matter. It moves the exact state of a system by using a pair of entangled partners and a classical message that carries the result of a joint measurement. The protocol respects causality because reconstruction at the destination is impossible until the classical data arrives. Nothing useful appears earlier than allowed, which keeps the past safe while still achieving a miracle of perfect state transfer. As an engineering pattern, teleportation is a building block for networks of quantum devices. It enables relocation of fragile states across noisy channels by swapping entanglement rather than by fighting to keep coherence alive during transit. Repeaters that chain this process promise continent-scale quantum links that deliver states on demand to distant laboratories. For time travel enthusiasts, the lesson is twofold. First, entanglement is a resource as practical as fuel, when the goal is to coordinate distant actions at the edge of what physics allows. Second, every useful protocol so far finds a way to be astonishing while refusing to break no signaling. The path forward likely lies in multiplying such protocols until the combined effect feels like a soft form of temporal flexibility. Over the next decades, the image of time manipulation will likely look like a control room that routes entanglement and classical bits with exquisite timing, rather than like a door glowing in the air. The romance is different, but the power is real. 40. Post-selected experiments seem to sculpt histories after outcomes are known. In a post-selected ensemble, one discards all trials that do not end in a chosen outcome, and then analyzes only the survivors. The statistics of the survivors can display patterns that look as if the future selection reached back and edited the past. In reality, nothing has been sent backward. The selection simply cuts out histories that do not fit the final condition, and the remaining set acquires structure that mimics retroactive influence. This method has practical teeth. By committing to keep only successful patterns, the measurement can be made more sensitive to rare signals. In quantum information, it can amplify tiny effects into readable shifts without adding much disturbance. In fundamental tests, it stresses classical intuitions by showing how much of what we call cause is an artifact of which records we keep. For a designer, the key is discipline. Post-selection can fool the unwary into thinking that a performance boost is universal when it is conditional. Systems built on this method must integrate the cost of discarded trials and must avoid sliding into paradox by claiming an unconditional gain. When the accounting is honest, the method becomes a scalpel for shaping the apparent flow of events inside a data pipeline. This is a kind of temporal carpentry. One does not hammer nails into time. One cuts away branches of history in the bookkeeping so that the displayed story has the contour one needs. The world remains causal. The narrative becomes artful. 41 Shwi. Cosmic microwave background photons are a memory of an infant universe. These ancient photons last scattered when the cosmos cooled enough for atoms to form and have been traveling largely undisturbed ever since. They carry a snapshot of density ripples that later grew into galaxies and clusters. By mapping tiny temperature and polarization variations across the sky, we reconstruct not only a picture of space, but a timeline written into the radiation itself. The light is a memory, and the cosmos is an archivist that never forgets. Time travel through observation begins here. We do not visit the past with bodies. We invite the past into our detectors by catching messengers that have been en route for billions of years. The remarkable point is that the record preserves not only positions, but phases and correlations that encode the early clock of the universe. Reading those phases is equivalent to reading the minute hand on a primordial watch. As instruments sharpen, they extract more of that memory. Polarization patterns reveal gravitational lensing accrued along the path, which turns the photons into reporters about everything they passed. Spectral distortions would reveal any energy injections long after the initial emission, which adds footnotes to the record. Every improvement in sensitivity is a deeper excavation of time. For the narrative of temporal engineering, this is the gentle path. Before we bend time, we can mine it. The universe has recorded its childhood with such care that our best investment may be to keep building better readers before we fantasize about building corridors. 42 baryon acoustic oscillations encode a metronome of early cosmic time. In the hot plasma before atoms formed, sound waves rippled through the coupled fluid of light and matter. When the plasma cooled, the waves froze into a preferred separation scale that later guided where galaxies were more likely to form. That scale shows up today as a subtle bump in the correlation of galaxy positions and serves as a standard ruler across vast distances. The ruler is also a clock, since its imprint depends on the timing of events in the early plasma. By measuring this scale at different epochs, we reconstruct how the expansion rate changed, which is equivalent to tracking the cadence of cosmic time. The method cross checks inferences from the cosmic microwave background and from supernovae, and it anchors our understanding of dark energy, which sets the long-term tempo. Each new survey adds bars to the cosmic score and tightens our grasp of when and how the rhythm evolved. Engineering here is about instrumentation and statistics. Telescopes must collect vast catalogs with controlled systematics. Algorithms must extract a weak feature from noisy data while accounting for lensing, bias, and selection effects. The reward is a robust yardstick that does not require assuming the detailed properties of galaxies, because the imprint was laid down long before those galaxies had complex lives. Time travel talk often leaps to portals. The baryon-acoustic ruler is a reminder that the first triumph is to build clocks and rulers that reach across the universe and return with answers about when. With tools like this, we do not conquer time. We converse with it. 43. Inflation may have stretched quantum fluctuations into classical history. A brief era of accelerated expansion is thought to have blown microscopic quantum jitters up to cosmic scales, freezing them into the seeds that later became structure. If this story is accurate, then every galaxy is the fossil of a quantum fluctuation, writ large. That is a breathtaking merger of the smallest and the largest, and it says that the randomness in our night sky began as uncertainty at the base layer of reality. The fingerprints of this process include nearly scale invariant variations in the cosmic microwave background and a specific pattern of correlations between different angular scales. A distinctive curl pattern in polarization would be a smoking gun from primordial gravitational waves, though the search is hard because later dust and lensing can mimic the signal. Each improvement in foreground cleaning and detector sensitivity narrows the possibilities. Inflation also raises deep questions about time itself. Exponential expansion erases memory of earlier conditions, which means the arrow of time during that phase is brutally one way. It also threatens to be eternal in some models, producing a multiverse where pocket universes bud off indefinitely. If so, the meaning of before and after becomes slippery across the full ensemble, and our local time may be a regional rule rather than a universal law. For engineers and storytellers, the lesson is that the greatest editor of time in our cosmos might have been a brief blast that none of us remember. If we ever learn to mimic even a hint of that control in a laboratory, we will have a lever that moves more than seconds. We will have a lever that moves history. 44. A big bounce could replace a beginning with a prior contracting phase. Instead of a singular start, the universe may have undergone a contraction that reversed into expansion when quantum gravity effects stiffened the equation of state. In such models, time does not begin at our Big Bang. It passes through a bottleneck. Structures from the previous era may leave faint echoes in the current one through imprints on long wavelength modes or through relic particles that survive the squeeze. A bounce reinterprets the arrow. During contraction, entropy still grows, but volume shrinks so that complexity compresses into denser forms. At the reversal, much of that complexity may be wiped clean, yet some correlations could thread the needle and seed the next expansion with memories. Detecting these would require heroic measurements of the largest scale correlations and an iron grip on systematics. The idea matters because it trades metaphysical questions about creation for physical questions about transition. Instead of asking why time began, we ask how physics behaves at densities where classical pictures fail. Competing scenarios make different predictions about the statistics of primordial perturbations, the presence of non-Gaussian features, and the behavior of gravitational waves across the bounce. If a bounce is real, then the most ancient form of time travel is simply attention to the right data. We would not build a machine. We would read a scar. That scar would tell us that even time has a biography with chapters older than we imagined. 45. Cyclic cosmology imagines time as iterative rather than linear. Some models propose that the universe undergoes endless cycles of expansion and contraction, or of quiescent eras punctuated by rejuvenation events. Each cycle resets large-scale conditions while passing forward a subset of information that survives the turnover. Time becomes a circle with texture rather than a line with a start and a finish. The appeal is that it explains low initial entropy by placing our present in a long sequence where special states occur naturally at each renewal. Observationally, this vision competes with inflationary narratives and must match the same successes while adding distinctive predictions. Possible signatures include subtle alignments at the largest angular scales, a specific distribution of cluster formation times, or relics with lifetimes that span multiple cycles. Extracting such hints demands surveys that link precision with reach and demands theoretical work that turns poetry into testable curves. Philosophically, the cyclic view softens despair about ultimate endings and beginnings. If the cosmos breathes, then every loss is also preparation for a new inhale. Agency acquires a strange echo, since acts that seem transient may leave fingerprints that echo far beyond a single cycle. Ethics and meaning are not the focus of physics, yet the narrative that science tells shapes how cultures imagine their place in time. For builders, the most direct consequence is pragmatic. If the universe likes cycles, then devices that respect rhythms may find more sympathetic niches than devices that fight for linear dominance. Clocks synchronized to natural beats, energy storage that rides on environmental oscillations, and computing that exploits periodic resets become first-class citizens. The rhythm of the cosmos becomes a quiet mentor for human timing. 46. Conformal cyclic cosmology maps the remote future onto a new Big Bang. In this proposal, a universe that has expanded into a cold, dilute state can be rescaled so that its far future resembles the hot, dense beginning of another epoch. The trick relies on the fact that physics at extreme scales can become insensitive to absolute size, so that a universe with almost no massive particles left can be stretched and relabeled as the fresh start of a new aeon. Time then becomes a chain of eras where the end of one is mathematically glued to the birth of the next, in a way that hides the seam from local observers who only see their own slice. Evidence is sought in delicate patterns. Within the oldest light, we can measure where small circular features might betray collisions between remnants of black holes from a prior eon and the newborn plasma of ours. The search is difficult because foreground dust, lensing, and instrumental noise can imitate such rings, and because the statistical significance required is severe when one is combing through billions of possible patterns for a handful of genuine scars. Negative results so far do not kill the idea, yet they push its predictions into corners that require sharper instruments and cleaner skies. If the mapping is real, it softens the terror of a heat death by turning it into a metamorphosis rather than an ending. Information that survives in subtle radiation fields would become the seed vocabulary of the next cycle, while most details dissolve into uniformity. The arrow of time remains within each eon because entropy still grows from a very special start, yet the chain as a whole evades a single beginning and a single finale by breathing through an infinite sequence of conformal breaths. For engineering imagination, this narrative suggests a strange, long game. Civilizations in the deep future might choose strategies that hide information in carriers that survive into the conformal handoff, such as very low-energy photons spread across vast distances. If even a trace can leak across the seam, then a message could echo into the next dawn, not by jumping through a portal, but by surfing the rescaling that stitches eons together. 47. Dark energy may alter the long-term meaning of duration. The measured acceleration of cosmic expansion means that distant regions recede faster and faster, so that communication horizons grow, and many galaxies fade beyond reach forever. This changes what it means to wait, because there will be events that no amount of patience can bring within view. and conversations that can never be resumed once the separation crosses the horizon. The universe becomes a patchwork of islands that age in partial isolation, where local clocks tick on, yet the shared stage shrinks for each island to its own neighborhood. On vast timescales, the acceleration also redshifts background radiation to irrelevance, and star formation dwindles as gas is consumed or locked away. Astronomers in far futures will not see the same sky we do, and their reconstructions of history will be limited by a dearth of long-range messengers. Duration itself becomes provincial, because records fade not only through entropy, but through the geometric loss of contact with the rest of the cosmos. Waiting ceases to be a strategy for learning the big picture. For technology, this pushes value toward archives and toward local completeness. Instruments must capture and preserve the data flows available now, because many will become unrepeatable. Power systems must be designed to sip energy across ever longer nights as environments grow cooler and dimmer. Communities must cultivate culture that makes sense when news from the deep sky stops arriving, because the horizon has outrun every carrier that could bring it. For time-traveled dreams, the lesson is harsher patience. The far future is not an endless opportunity to watch more, but a regime where less can be seen no matter how long one waits. If a society wishes to speak across deep centuries, it must use channels that will not be torn apart by acceleration, and it must accept that many conversations are already ending, even as we begin to notice that they had started. 48. Phantom energy could drive a big rip that tears time apart. If the accelerating agent has an equation of state that is more negative than the vacuum energy of a simple cosmological constant, then expansion accelerates so violently that bound structures are ripped apart in a finite time. Galaxies unbind, stars are stripped from systems, planets are torn from stars, molecules fall to pieces, and finally tides from the runaway scale factor defeat any attempt by matter to hold together. Time ends not in a slow fading, but in a crescendo, where the meaning of proximity and sequence loses coherence. The timeline for such a catastrophe depends on the precise value of the parameter that links pressure and energy density for the dark component. Current observations allow values close to the cosmological constant, but the uncertainty leaves room for a phantom possibility that would deliver a big rip in a large but finite number of billions of years. Better maps of distance measures and structure growth are slowly squeezing the room, yet have not nailed the value to the simple case beyond all doubt. Survival strategies for intelligence in such a world look grim, because even protected vaults and artificial gravity would eventually fail when the underlying space-time forces particles apart. The only plausible refuge would be to discover a mechanism to alter the equation of state locally, or to migrate into regions where the effective behavior differs due to interactions we do not yet understand. That is a tall order, which is why most plans focus on measurement rather than mitigation. Phantom scenarios are extreme, yet they function as thought experiments that teach humility. If the fabric can betray all bonds, then engineering must learn that some endings are not negotiated. The proper response is to learn faster while the universe is still friendly, and to build instruments and archives that can harvest and protect meaning before the ledger of moments stops being legible. 49. Black hole evaporation raises the puzzle of where information about time goes. Quantum effects predict that black holes radiate with a temperature inversely related to their mass, and that over immense spans they lose mass and vanish. If all that remains is featureless radiation, then the detailed record of what fell in seems lost, which collides with the principle that quantum evolution should preserve information. The riddle is not only about spatial details, but about temporal order, because the interior history appears to be erased from the outside, as if a chapter were burned rather than archived. Progress came from recognizing that the flow of entropy in the radiation does not climb smoothly, but bends late in the process so that information can leak out in correlations as the whole shrinks. This curve was derived using powerful arguments from holography, which treats the interior as encoded on a boundary, and from models where explicit calculations are possible. The lesson is that what looked lost may have been scrambled into patterns that are fiendishly hard to read, yet are present in principle. Experiments are impossible for astrophysical wholes, but laboratory analogs can mimic horizons for sound or light and allow study of how excitations are created and how correlations spread. These do not settle the cosmic case, yet they sharpen methods and intuitions. Observationally, measuring evaporation from small primordial holes would be a triumph, yet the signatures are faint and the sky is noisy with other bursts that can mask or imitate the desired signal. For time and travel, the message is clear. The universe guards consistency by hiding information inside non-trivial encodings rather than by deleting it. A future time machine that respects physics will almost surely operate as an encoder and decoder of histories, not as a blade that cuts and pastes them. The craft will be cryptographic as much as mechanical. 50. The holographic principle treats space-time history as a boundary record. In many approaches to quantum gravity, the amount of information inside a region scales with the area of its boundary rather than with the volume. This hints that the entire evolution within can be described by degrees of freedom living on the surface which somehow project a three-dimensional and temporal narrative into the interior. The picture is as shocking as discovering that a novel carved into a shell somehow tells a rich story when read by the right light. This principle turns questions about deep interiors into questions about edges and makes geometry feel like a code rather than a stage. In certain cases, a precise duality relates a gravity theory in a bulk to a quantum field theory on the boundary, which means calculations about time flow, and black hole evaporation can be translated into calculations about correlation functions in a lower dimensional world. What looked like paradox becomes an accounting problem with a ledger at the edge. For engineers, this is not directly a blueprint, yet it whispers about how to build resilient systems, store the crucial state on surfaces that can be repaired and checked, encode bulk behavior in boundary controls that are easier to audit and synchronize. Use error correction not as a bandage, but as the actual language of construction in which the interior performance is guaranteed by the structure of the exterior checks. Time travelers in fiction step through doors. Time engineers in a holographic world would polish the door frame. The power would reside in how well the boundary is prepared and how perfectly its dynamics shepherd the interior tale, whose pages are read as seconds by those who live inside. 51. Page curves suggest information returns from evaporating holes late in time. The entropy of radiation emitted by a black hole initially rises because early quanta carry almost no detail about what fell in. Later, if unitarity holds, the entropy must peak and then decline as correlations begin to carry information outward. The graph of this process is the page curve, and its shape has become the standard by which proposals are judged. A theory that cannot produce the right bend and fall is suspected of hiding a violation of quantum consistency. Recent work uses replica methods and ideas from quantum extremal surfaces to compute the curve in controlled settings. The surprising result is that the calculation seems to require including regions that behave like islands inside the gravity theory, which contribute to the entropy seen by an outside observer. The mathematics is dense, but the story is vivid. The bookkeeping must count parts of the interior as if they had already been claimed by the radiation field when viewed from far away. These results do not yet translate into lab devices, yet they change the philosophy of information flow. What appears to be trapped by geography may already be in the ledger of a distant system if correlations stitch the two together. Storage, transmission, and retrieval become global operations defined by extremal principles rather than local transport. In such a world, the route to manage time is to manage where the surfaces that define entropy are drawn. This is the deeper moral. If information can be accounted for across regions that are not naively connected, then time can be shaped by moving boundaries in the informational sense rather than by moving mass. The future of temporal control may look like the art of drawing the correct islands in the sea of states. 52. Firewalls would break the smooth experience of falling through. One proposed resolution of the black hole puzzle is that the horizon is not a benign surface but a searing boundary wherein falling observers encounter violent excitations that shatter the gentle passage predicted by classical theory. This firewall would sacrifice the equivalence principle in order to preserve the purity of quantum evolution by keeping interior and exterior descriptions from coexisting peacefully. The cost is high because the smoothness of the horizon is a cherished feature of general relativity. If firewalls exist, they would replace the quiet drift into darkness with an abrupt end to any experiment that tries to probe the interior. Observationally, we would expect signatures in gravitational wave echoes or in the detailed statistics of light near the edge because the behavior of matter approaching the horizon would change. So far, the data do not demand such a radical revision, yet the questions remain open and are sharpened by each new image and waveform captured by our instruments. For time narratives, the firewall is a stern warning about limits. There may be boundaries that are not negotiable and that enforce a single story by destroying attempts to write two. A device that tries to maintain both an interior continuity and an exterior record might be impossible because consistency forces one or the other to break. That constraint channels design toward protocols that never require a traveler to straddle incompatible descriptions. The concept also reminds builders to budget for safety. If a region of space-time can flip character from smooth to lethal because a consistency threshold is crossed, then cautious operations will stay well away from such thresholds. Temporal engineering will be aerospace with extra layers of respect for invisible limits that only mathematics can plot in advance. 53. Complementarity tries to keep both inside and outside stories consistent. An alternative to drastic walls proposes that no single observer can witness a contradiction because the descriptions available inside and outside a black hole are complementary views that never need to be merged into a single global film. The unfollower sees a smooth passage. The distant astronomer sees radiation that eventually reveals the information, and there is no paradox because no one can compare the two full records across the barrier. Nature saves consistency by limiting which stories can be told together. This move has precedent in quantum mechanics, where incompatible measurements cannot be assigned simultaneous definite values. It extends that lesson to gravity by treating horizons as separators of narratives rather than as objects that must carry one unified account. The mathematics remains demanding because one must show that all predictions agree where they ought to, and that no sneaky observer can build a setup that forces a clash. For technological imagination, this view suggests a practical ethic. Design systems so that each observer frame has a clean and self-consistent story, and do not despair if no omniscient viewpoint exists. Communication protocols, security models, and legal frameworks already adopt similar rules when they restrict who can access which records and when they allow reconciliation only along approved channels. Physics seems to endorse this modularity at the deepest level. Time travel dreams then inherit a boundary culture. Devices must allocate who gets which facts and must prove that no combination of channels allows a paradoxical composite. Success will look like architectures where every participant holds a full truth locally, while the global truth is not a single tapestry, but a quilt of consistent patches. 54. Traversable wormholes in certain theories mimic quantum teleportation. Work that couples two black holes in a carefully arranged way shows that signals introduced on one side can be recovered on the other if the coupling is tuned and timed just right. The mathematics reveals that this process is closely related to quantum teleportation, where entanglement and a classical message allow perfect state transfer. The gravity picture becomes a vivid geometric metaphor for a protocol that was already known in quantum information, yet now appears as a bridge in space-time. The insight does not hand over a quick route through the stars, because the coupling must be engineered in a theory space rather than in a machine shop, and because causality remains respected by the need for the classical communication step or its gravitational dual. Nevertheless, it changes how we think about connections. What looks like a tunnel may be a visual story for an algorithm that rearranges correlations and surfaces to shepherd a state from here to there without carrying substance in the usual sense. Engineers can draw lessons even before full unification arrives. Teleportation inspires network design, where entanglement is pre-shared and where paths are defined by who shares with whom, rather than by physical conduits. Error correction becomes the spine because without it, long chains fail. Timing is the blood because windows for successful swaps open and close quickly in realistic environments. If wormhole metaphors help us organize these networks, then travel across time and space will look like orchestration rather than motion. People will still move slowly, while states and decisions flow instantly within the rules. The romance remains, translated into a language that routers and clocks understand. 55. Quantum gravity may quantize time as well as space. Most approaches to unifying the small with the massive suspect that continuity is an approximation. If areas and volumes have discrete spectra, then durations may also come in quanta, so that evolution is a sequence of hops, not a glide. The continuous equations we use would then be effective tools that ignore the clicks under the hood the way thermodynamics ignores the jitter of molecules when it writes smooth curves for pressure and temperature. Detecting the clicks requires sensitivity to phenomena where a tiny mismatch from perfect continuity would accumulate into a visible phase error or into a noise floor that refuses to decline with better engineering. Astronomical baselines help because long paths magnify delicate effects. Laboratory interferometers help because their coherence times have grown to astonishing lengths. So far, the clicks hide or are too soft to dent our graphs. If the discreteness is confirmed, it would give designers a new set of knobs. Devices could lock onto preferred durations, the way superconductors lock magnetic flux into quantized packets. Out-of-tune processes would damp, while in-tune ones would resonate, leading to clocks that anchor themselves to the grain of time rather than to external references. Networks could synchronize by counting shared ticks from the fabric itself, with accuracy that outlives any individual node. The cultural shift would be profound. Humans grew up with time as a river. A confirmed quantum would reveal that it is a staircase. Walking a staircase invites different strategies than swimming a current. We would build landings, rails, and steps that fit the stride of the universe. 56. Loop quantum gravity replaces continuous time with spin network updates. In this framework, geometry is encoded in webs whose links carry discrete units of area and whose nodes carry discrete units of volume. Evolution is represented as a foam, where networks change in quantized moves rather than through differential equations over smooth fields. The picture is combinatorial and austere, yet it reproduces familiar space and time, when the networks are large and tangled enough that averages smooth the angles and steps. The approach shines near places where classical theory predicts infinities, such as the centers of black holes or the initial singularity. There, the granular rules halt the runaway by never allowing volumes to shrink below certain minima. Time does not fail. It reverts to its native stepwise character. Predictions include bounces, where collapse rebounds into expansion inside horizons, or where early universe contraction flips into growth before densities diverge. For experiment, direct tests remain distant, but the framework motivates searches for subtle imprints in gravitational waves, in the polarization of the oldest light, and in the spectrum of tiny black holes, if any formed in the early universe. It also guides algorithmic thinking in simulation, where updates become graph rewrites rather than solutions of partial differential equations. That shift fits well with the rise of discrete computing and of architectures that operate natively on graphs. If the world is a network, then time control translates into update scheduling. Engineers would learn to shape when and where rewrites happen to create corridors of effective slowdown or speed up within the foam. The imagery discards the tunnel for the switchboard and invites a generation to master the art of routing causality through graph moves. The fundamental actors are not points, but one-dimensional strings and higher-dimensional brains that vibrate in ways that we perceive as particles and forces. Time is one of the coordinates on which these objects oscillate, and in many solutions, additional spatial dimensions are compact or warped, so that the effective behavior in 4 dimensions hides a richer playground. The geometry can curve in ways that create throats, folds, and mirrors, whose interpretation in lower dimensional language looks like forces and fields changing with time. Dualities relate different descriptions that seem unrelated at first glance and sometimes trade a strongly coupled, messy view for a weakly coupled, clean one. Among these dualities are those that blur the distinction between time evolution and renormalization flow, which suggests that some aspects of duration can be reimagined as changes in description rather than as changes in reality. This makes time feel like a coordinate we learn to translate rather than a single universal beat. Testing string ideas directly is hard because the scale where the strings reveal their length is far beyond current colliders. Indirect tests look for features such as specific spectra of gravitational waves from early processes, for cosmic defects like strings stretched across the sky, or for patterns in particle couplings that betray extra structure. The theory has delivered deep mathematics and a web of relations that guide thinking, even when experiment lags. For time travel builders, the payoff today is conceptual tools. Bruns, sliding in warped throats, teach how motion in hidden directions can look like large changes in familiar time. Metaphors from dualities teach how to reroute problems into pictures where progress is easier. The route to bending time may be to find the right translation rather than the right engine. 58. Extra time dimensions would revolutionize causality if they exist. Physics so far treats one time dimension as plenty because adding another invites contradictions, such as closed time-like paths that are too easy to draw and instabilities that wreck predictions. Nevertheless, speculative models have explored the possibility in controlled ways, hoping to gain new handles on unification or to explain anomalies. If there were even a hidden trace of a second temporal direction, it would rewrite how we define cause, effect, and the allowed structure of motion. Observational constraints are fierce because additional time would typically show up as violations of cherished symmetries or as new kinds of particles with weird dispersion that we do not see. Stability conditions in quantum field theory also push hard against such options by turning small fluctuations into runaway catastrophes when too many temporal directions are allowed. The silence of the data so far is a strong argument for the simplicity of one. Yet thinking through the consequences is not wasted because it trains intuition about what makes our world consistent. The discipline of discarding tempting but fatal freedoms refines the space of viable models and clarifies why some desires must remain in fiction. It also suggests that any successful time technology will operate inside tight bounds, because nature seems to abhor extra-temporal freedom even at the level of equations. If a shadow of another temporal axis lurks anywhere, it will be revealed first as a constraint violation in precision timing experiments or as an energy instability in systems that should be quiet. Until such a crack appears, prudence says to build within the proven corridor of a single time, and to celebrate how much richness has already been found within that narrow but generous lane. 59. Brainworld scenarios allow time to flow differently across brains. In models where our visible universe is a membrane embedded in a higher dimensional bulk, gravity can leak between brains, while other forces are confined. If time is tied to how fields propagate on each brain, then different brains could experience different effective rates or different arrows depending on their content and geometry. Interactions through gravity would then be conversations across layers where clocks do not agree, a tantalizing setting for tales of misaligned eras. Phenomena such as modified gravity at large scales, Kaluza-Klein echoes of gravitons, or deviations in cosmic expansion can serve as hints that we live on such a sheet. So far, measurements lean in favor of simpler pictures, yet leave windows open that motivate further surveys and clever laboratory probes. The appeal is that such scenarios might explain puzzles like the weakness of gravity, while offering testable deviations at the percent level in carefully chosen regimes. For engineering, even a weak coupling to another brain with a different tempo would be a treasure. One could imagine parking data, or even biological tissue where external time races ahead or lags behind, while subjective time on our side remains comfortable. Security, ethics, and control would dominate the discussion, because the temptation to arbitrage across time differences would be enormous. Absent evidence, the practical value is metaphor. Treat networks, clouds, and jurisdictions as brains with different latencies and rules, then design protocols that move work to where the effective time is right for the task. A culture that becomes fluent in crossing between such layers will be better prepared if nature turns out to have built real layers into the cosmos. 60. The speed of light as a constant anchors causality in special relativity. Every scheme to bend time must live under the ceiling set by a universal speed beyond which influence cannot propagate in a vacuum. This limit is not just a property of light, but a conversion between space and time, woven into the fabric of how measurements transform between observers in motion. It is the reason clocks in different frames disagree in predictable ways, and the reason sequences that look different to different observers are reconciled without contradiction. Experiments keep hammering on this anchor and find it unyielding. High-energy particles from distant astrophysical blasts arrive within narrow spreads. Laboratory measurements of the propagation of electromagnetic waves show no drift with direction or season, and the working of global navigation depends on formulas that would fail catastrophically if the limit wobbled. The anchor holds across scales and environments, which is why it has earned the status of a principle rather than a hunch. For designers, the constant is not an enemy, but a ruler. It defines what can be synchronized and what must be cued. Systems that respect it can be made robust because they do not rely on fragile conspiracies of timing to beat the limit. Paradox creeps in only when one pretends the limit does not exist, or when one confuses correlations with communication. Everything ambitious that works in modern quantum networks and in relativistic navigation is built with this humility. If time travel is ever achieved, it will be by playing within the geometry that this constant defines, rather than by smashing through it. Shortcuts will be curves in the fabric or encodings in the information that rides on the fabric, not violations of the limit itself. Accept the anchor, and the sea of possibility remains vast. 61. Doubly special relativity introduces a shortest length and a modified timing. This framework keeps the universal speed while adding a second invariant scale usually tied to the Planck length, which forces transformations to respect both a fastest influence and a smallest structure. The result is a gentle deformation of how momenta and energies add, which then nudges how clocks compare when frames move fast. Over astronomical baselines, such nudges could accumulate into phase shifts that betray the hidden scaffold, even if everyday devices notice nothing unusual. The precision timing of distant flashes and interferometry with extreme stability become probes that listen for the soft click of a minimum grain. For engineering imagination, the existence of a second invariant teaches a new way to design standards, because reference devices would not rely only on velocity, but also on a built-in microscopic yardstick. Networks could anchor their synchronization to patterns that cannot be stretched past that scale, which yields resilience against certain drifts and tampering strategies. Cryptographic protocols might encode bits in combinations of rate and grain, so that forgery fails unless both invariants are respected at once. If nature uses such a rule book, then attempts to stretch timing beyond the grain will waste energy and create heat without adding fidelity, which sets a hard economic limit on metrology. The rational response is to find resonances that align with the deformation so that devices sing rather than fight, and so that power is spent pushing useful harmonics rather than creating noise in forbidden bands. This is how designers adapt when a new constant enters the stage. Time travel ambitions narrow rather than vanish because deformations tend to preserve causality while changing the bookkeeping. You still ride within the cone, yet the edges of the cone pick up curvature that can be budgeted like a small tax. A civilization that writes its schedules with both speed and grain in mind could still build corridors of dramatic time contrast without ever breaking the anchor that keeps paradox away. 62. variable speed-of-light proposals would rewrite temporal history. Some models allow the limiting speed to drift in the very early universe, which could solve puzzles normally addressed by rapid inflation, by letting distant regions exchange influence more easily in the past than they can now. If light once ran faster, then clocks and rulers inferred from ancient messengers would need recalibration, which changes the story we tell about when structures formed and how long processes took. These ideas are tightly constrained because too much drift would spoil the excellent fits already achieved by standard cosmology. Testing the concept leans on cross-checks between independent cosmic chronometers, such as supernova light curves, baryon acoustic scales, and primordial elementy abundances. Laboratory bounds arrive from comparisons of different atomic transitions over long periods, which can reveal whether dimensionless combinations that include the speed have shifted. The weight of evidence so far supports constancy within tight error bars, yet explorations continue because even a tiny early-era deviation would have outsized consequences. If a small window of higher speed existed, then the cosmic archive is full of subtle fingerprints waiting for clean extraction. Polarization patterns, dispersion of high-energy photons, and statistics of lensing. Each carry traces that together can either close the door or keep it ajar. The pursuit forces better instruments and deeper catalogs which enrich astronomy regardless of the verdict. For time-travel dreams, this path is more cautionary than enabling. A variable limit would mostly be an ancient gift rather than a modern lever, and trying to reproduce it today would require energy densities and states of matter far from safe practice. The wisdom is to learn from the past about what is possible in principle, while designing tools that work within the serene constancy we inherit now. 63. The equivalence principle unites acceleration and gravity into one temporal effect. Locally, an accelerating elevator and a small room in a weak gravitational field are indistinguishable to experiments that fit inside, which means that clocks feel gravity as if it were acceleration and feel acceleration as if it were gravity. This bridge explains why time runs slower lower in a field, and why time also runs slower on a rocket that pushes hard for long enough, which simplifies design, because a single principle predicts both outcomes. Devices that exploit one can be translated into devices that exploit the other by changing hardware rather than theory. Navigation systems already honor this unity by correcting satellite clocks for both their altitude and their orbital motion, so that maps land where drivers expect. Laboratory drop towers extend the lesson by placing atomic clocks and interferometers in freefall to peel gravity away from acceleration and to measure the residue, which refines the equality to an impressive degree. Each refinement tightens bounds on new physics and tightens the tolerance budgets of instruments that live near the edge of sensitivity. Engineering opportunities bloom wherever sustained acceleration is available, because a craft that delivers comfortable push for months becomes a clock sculptor in its own right. Compute racks, chemistry stacks, and even biological cultures on board can be paced relative to the outside world simply by flying the right profile without any special gravity source. This converts propulsion from a way to change position into a way to change the rate at which internal stories are told. Time travel remains forward only under this principle, yet the control is real. One can bank years of external time with steady push and then return to a world that has aged without the crew, all while every equation stays within conservative physics. The challenge is engineering long burns rather than discovering new laws. 64. Gravitational waves transport changes in the geometry of time. These ripples stretch and squeeze space-time as they pass, so that the separation of free-floating objects rhythmically increases and decreases, which means that not only distances, but also local rates of ticking are modulated during transit. Detectors that measure phase over long arms are in effect listening to a temporary rewrite of their calibration by the wave, which is a rare direct experience of time being edited by nature. The waves we have caught come from collisions of compact objects, where gravity is at its most musical. Future instruments in space will hear lower notes from supermassive mergers and backgrounds from the first seconds after the hot beginning, which turns gravitational astronomy into a clock laboratory that spans the cosmos. Networks of pulsars already serve as timing arrays that reveal a slow undulation across the sky, and each improvement in cadence and precision turns more of the background into a readable score. The universe conducts, and we translate its baton movement into numbers. For technology beyond astronomy, the lesson is synchronization under disturbance. If your clocks can track and reject the faint tempo imposed by cosmic waves, then they are robust against almost any terrestrial noise as well. This informs designs for finance, communication, and control, where nanosecond alignment matters, and where nature's smallest shoves must not tip systems into error. Instruments that survive a passing ripple in time geometry will survive nearly anything. The dreamier consequence is conceptual. If waves can alter the shape of time for a moment, then geometry is not a frozen container but a participant that can be driven. We do not yet push back with comparable force, but the existence of a handle, however weak, is enough to justify devotion to better grips. 65. Timing arrays use pulsars to map subtle tremors in cosmic time. Millisecond pulsars are neutron stars that spin with astonishing regularity and fold their rotation into radio flashes that work as natural beacons. By timing many of them across the sky and comparing arrival patterns over years, one can see correlated drifts caused by long wavelength gravitational waves, and perhaps by other slow modulations of the metric. This converts the galaxy into a detector whose arms are light years long and whose mirrors are spinning remnants of dead sun. The engineering battle is fought against noise from interstellar plasma that delays radio waves and from intrinsic wander in individual pulsars that must be modeled and subtracted. International collaborations build receivers with bandwidth and stability that would have stunned earlier generations and build software that knits together data from different telescopes into unified streams. The result is already a detection of a stochastic background that appears to hum beneath the radio sky. With patience, the map will sharpen into a catalog of sources and a measurement of the spectrum that constrains theories about how black holes pair and merge, and about how early processes may have rattled the fabric. Each improvement also feeds back into precise ephemerides that benefit navigation and tests of gravity in strong fields, which broadens the return on the investment. The sky becomes both an observatory and a timing backbone. Time travel hopes do not ride directly on pulsars, yet the discipline they enforce is exactly the discipline any serious temporal engineering will require. You must keep honest books over decades, cross-check with independent clocks, and model every nuisance that tries to sneak into the ledger. Master that culture, and you are ready to notice the small doors if they exist. 66. Precision atomic clocks reveal gravitational time shifts across centimeters. Optical transitions in trapped ions and neutral atoms form clocks so stable that lifting one by the height of your hand changes its tick rate by a measurable amount, which converts a lab bench into a topographic map of time. Linking many such clocks by fiber turns cities into arrays that see tides, groundwater changes, and even the pressure of weather patterns as gentle tilts in the flow of seconds. Geodesy becomes a branch of timing rather than only of surveying. This capability opens industries that trade in temporal gradients as resources. A data center could park latency-sensitive tasks where time runs slightly faster and reserves slower zones for bulk processing that cares more about energy than about speed. Banks could audit contracts with stamps referenced to gravitational potential, so that fairness is enforced even when parties operate at different altitudes. Hospitals could coordinate radiation therapy with phase coherence tied to the same reference, so that dosing gates at exactly the intended instance. Scientific payoffs include comparisons of fundamental constants across long periods and across environments which challenge theories that predict tiny drifts. Networks can hunt for dark matter that couples to clocks by watching for correlated blips that sweep across countries like invisible weather. Space missions can fly clocks as science payloads and return maps of planetary gravity with resolution set not by cameras, but by seconds. For time-travel discourse, the moral is steady. Before anyone folds an era build the habit of measuring time so precisely that a building's elevator ride is an experiment. The culture of such clocks will train minds to think of seconds as fields rather than as numbers, which is the mental move required to shape them. 67. Underground clocks could map mass distributions through time dilation. Burying precision clocks and linking them to surface references turns subsurface density into a signal, because deeper clocks tick slower in proportion to the gravitational potential they inhabit. Mines, tunnels, magma chambers, and aquifers then reveal themselves as patterns in timing rather than as features in seismic echoes, which offers a complementary view that does not require shaking the ground. With enough instruments, geophysics becomes a quiet practice of listening to time rather than banging on rock. The technique scales to civil infrastructure by watching for sagging bridges or settling foundations through tiny changes in potential that accompany mass motion. Early warnings would arrive from the clock ledger long before cracks widen, which makes maintenance proactive rather than reactive. Insurance and public safety agencies can share timing dashboards that turn the invisible flow of seconds into a city-wide diagnostic. Scientific curiosity also wins because underground arrays near fault zones could detect slow mass creep that precedes slips and could map how water moves through fractured rock, which informs both earthquake science and resource management. Environmental monitoring gains a new instrument that does not disturb habitat and that works in darkness and silence. There is no portal here, yet there is mastery of context, which is a prerequisite for any deeper manipulation. To steer time, one must first see where it runs faster and where it pools, and how matter sculpts the contours. Underground clocks teach that mapping. 68. Satellite constellations already correct for relativistic time drift. Global navigation depends on timestamps from orbiting clocks that would drift out of usefulness within minutes if designers ignored the combined effects of motion and gravity. Before launch, the clocks are set to tick at a slightly wrong rate so that once in orbit they appear right to users on the ground, and continuous corrections maintain alignment as orbits breathe. Every successful route on a map is therefore a quiet celebration of relativity as applied engineering rather than as philosophy. The control rooms running these systems are temples of calibration, where atmospheric delays, multipath reflections, solar activity, and hardware aging all try to pull the network out of tune. Software and procedures push back with models and cross-checks that convert a chaotic radio sky into a stable grid. This culture demonstrates how to build global time, even when nature and cities conspire to scramble signals. Future upgrades will tighten orbits, add optical links that reduce radio noise, and introduce space-based atomic clocks of new designs that can be steered with lighter touch, which will in turn enable lane keeping for autonomous systems and safer aviation in crowded skies. Farmers, surveyors, and stock exchanges will piggyback on gains paid for by pilots and sailors because time is the shared utility hidden inside position. For time travel talk, the message is sober and optimistic. We already live inside a world where billions trust devices that reshape time into a coordinated service and where forward only relativistic quirks are tamed into convenience. Ambition should climb step by step from this proven base rather than leap off cliffs. 69. A navigation system becomes a laboratory when clock errors reveal gravity. When a timing network is dense enough and honest enough, the residuals that remain after standard corrections tell stories about the environment. Seasonal drifts trace water moving through mountains. Daily patterns trace human traffic that loads bridges and subways. Sudden steps reveal quakes or construction mishaps. The map app becomes a seismograph and a hydrologist and an urban planner because time is sensitive to mass and motion in a way few other signals are. Turning this into a formal instrument requires data rights frameworks that protect privacy while allowing aggregate analysis and requires algorithms that separate instrument drift from geology. Cloud services can run the inversions and push alerts to local authorities when the pattern of residuals crosses thresholds that correlate with risk. Insurance models update in near real time because the ground itself is in the data set instead of only weather and credit scores. Scientists gain a cheap global array that complements dedicated missions and that adds context to sparse but exquisite space-based gravity maps. Over years, the system will see glaciers thin, deltas sink, and aquifers empty, which rewrites our ability to budget water and to plan infrastructure with timelines that match reality rather than wish. The lever is modest, yet its reach is planetary. This is the ethic of near-term time engineering. Use the sensitivity of seconds to build services that save lives and money, while the quest for tunnels and loops continues in the background. Progress becomes a braid of utility and wonder rather than a single dramatic leap. 70. Quantum sensors may read space-time curvature through phase shifts. Matter waves accumulate phase as they move, and that phase depends on the path through the gravitational potential, which means interferometers built from cold atoms act as meters for curvature. Split a cloud, let halves drift along different trajectories, then recombine, and the resulting fringes encode the difference in experienced time. With shielding and clever design, such devices read tiny gradients that evade classical instruments, and they do so in compact packages. Arrays of these sensors could map gravity indoors, on ships, and from drones to build high-resolution pictures of mass distribution without digging or drilling, which transforms construction, archaeology, and security. By flying repeated surveys, one can watch changes over weeks and assign responsibility for subsidence or for illicit excavation with evidence rooted in physics. The sensors see through smoke and darkness because they listen to geometry rather than to light. Space missions will carry similar instruments to planets and moons, where they will map lava tubes, ice layers, and hidden seas that hide beneath crusts. Landers can drop pods that wake periodically, make phase comparisons, and sleep to save power, which grants multi-year records of how bodies flex and breathe. The same units can serve as inertial references for navigation when stars or radio beacons are unavailable. As one learns to read phase as time, the boundary between metrology and travel blurs. Even if no one steps through a portal, the ability to steer phase precisely and to decode it at will grants command over the order of operations in complex systems. Schedules become waveforms. Deadlines become interference peaks. The poetry becomes practical. 71. Cold atom. Interferometers can weigh time with interfering matter waves. Laser pulses act as beam splitters and mirrors for atoms cooled to near rest, and the resulting Mach-Zehnder-like loops measure acceleration and gravity with astonishing precision. Because phase is proportional to the integral of proper time along each arm, these devices are in fact clocks that compare routes rather than ticks, and their outputs are statements about how space-time treated two nearly identical parcels of matter. Noise that defeats classical accelerometers is filtered differently here, which gives complementary strengths. Field versions ride in trucks and aircraft to map gravity and to test foundations, while laboratory giants push sensitivity to new records and probe fundamental constants. Partnerships with optical clocks allow hybrid instruments where absolute time and relative time are fused into richer data streams that can isolate drifts and detect anomalies earlier. Maintenance crews learn to think like physicists, and physicists learn to package elegance into rugged boxes. The design space is still young, which means clever pulse sequences, new atomic species, and better vacuum and magnetic control keep unlocking performance without exotic materials. Each step tightens loops in control software that must schedule pulses, suppress vibrations, and cancel environmental shifts, which makes the whole stack a rehearsal for future temporal machinery that will have even tighter tolerances. The device teaches a social lesson as well. Precision flows from patience and from communities that share calibration tricks and error budgets openly. Time is a commons that rewards cooperation because no single lab can audit every nuisance alone. Travel in time will be a team sport if it ever becomes more than poetry. 72. Optical lattice clocks touch the instability of time at 15 digits. Atoms trapped in standing waves of light see transitions that can be interrogated for many seconds with laser fields so pure that the line width becomes vanishingly small, and the fractional stability reaches parts in 10 to the 18. Two such clocks, placed a step apart on a staircase, disagree just enough to measure the step, which turns architecture into physics class and physics class into architecture. Networks of these clocks define timescales that improve every few years as lasers and cavities are tamed. The bottlenecks now are blackbody shifts from the environment, collisional shifts from residual gas, and the quality of counting electronics that must not smear the purity with jitter. Cryogenic packages, better vacuum, and photonic integration continue to chip away so that the practical size and power drop toward deployable levels. Soon, power plants, labs, and ships will carry references that once fit only in national standards institutes. With coverage broad enough, one can attempt continental experiments that look for correlated blips from passing dark matter structures or for long, slow drifts in constants that theory allows at levels far below older detection limits. The clock grid becomes a new sense organ for the planet and for the sky, sensitive not to light or sound, but to the curvature of time itself. Time travel remains out of reach, yet the foundation grows. When society lives amid such clocks, the public will accept that seconds are not uniform everywhere, and that location and potential matter. That cultural acceptance is a hidden gatekeeper for any bolder steps. 73. A global network of clocks could sense passing dark matter through time jumps. If dark matter couples feebly to ordinary fields, it might still shift the energy levels that define atomic transitions, just enough to make synchronized clocks hiccup as a wave or compact clump drifts through. A single clock cannot separate such a blip from local noise, but a network that spans continents can look for patterns that move at galactic speeds and align along plausible trajectories. Timing becomes astronomy without telescopes and physics without accelerators. Data handling is the real challenge because petabytes of tick comparisons must be cleaned of mundane disturbances from power grids, weather, and maintenance schedules. Shared standards for metadata and open archives let many groups test hypotheses independently, which limits false alarms and accelerates discovery. The model follows seismology, where distributed sensors and community protocols turned earthquakes into well-understood phenomena. If a detection arrives, it will guide particle searches and cosmology by fixing properties like coupling strength and characteristic coherence length, which narrows candidate theories. It will also validate the idea that time is an exquisitely sensitive probe of unseen fields, which in turn inspires other networks tuned to different transitions and different species. Diversity becomes strength when nature might poke through any of several doors. The romance is subtle but deep. We learn about a galactic ocean not by looking for glitter, but by feeling tiny changes in the flow of seconds on our shores. Mastery of time reveals inhabitants of the dark that would otherwise remain forever anonymous. 74. The flow of time in a brain can be stretched by attention and threat. Human reports and neural recordings agree that perceived duration swells during emergencies and shrinks when minds are absorbed in rapid feedback tasks, which implies that the subjective clock is elastic and that its ticks are shaped by prediction and arousal. The underlying circuits involve neuromodulators that adjust gain and networks that compress or expand event boundaries when memory is written. Time as lived becomes a product of how the brain budgets surprise and expectation. This plasticity can be harnessed for training, therapy, and performance by structuring tasks that recalibrate rhythm without stressing the organism. Musicians and athletes already use drills that alter tempo and chunking to feel more time inside the same external window, and emergency responders rehearse under simulated stress so that dilation becomes familiar rather than frightening. Education can embed similar ideas so that learners feel spaciousness during hard problems rather than panic. Technology can partner with biology by delivering cues that nudge internal pacing through sound, light, and haptic patterns that entrain rhythms gently. Wearables that sense arousal can shift guidance dynamically so that overload recedes and flow states stabilize, which converts minutes into felt hours of productive engagement. None of this moves any external clock, yet it meaningfully changes life, because life is experienced from inside. The lesson for grander temporal dreams is empathy. If you cannot steward the time inside a human nervous system, you are not ready to steward the time inside a laboratory full of fragile states. Mastery scales outward from the self, and practices that dignify subjective time are part of the curriculum for any civilization that wishes to touch objective time. 75. Neural prediction makes the perceived present a carefully crafted delay. Signals from eyes, ears, and skin arrive at different speeds and are processed in different hierarchies, which would produce a jumbled now if the brain did not align them by delaying some and forecasting others. Experiments show that perception often reports events as if they happened slightly earlier than raw arrival would allow, which implies that the brain is drawing a best guess timeline and the backfilling details as confirmations land. The present, we feel, is therefore a stitched tapestry with threads that began in the recent past and arrows that point softly toward the near future. This stitching explains illusions where a late flash changes the story of a motion seen just before, and explains why audio synchronization in film must be tighter than casual intuition would predict. It also grounds the sense in which free choices are prepared by neural dynamics before they cross the threshold into awareness without abolishing agency, because the preparation is part of the choosing rather than a replacement for it. Minds are prediction engines that survive by painting time onto noisy data. Designers can work with this by delivering interfaces that respect the integration window rather than fighting it. Systems should align visual and haptic cues within the tolerance of cortical binding, and should schedule critical alerts to land within phases where attention can reset cleanly. When tools harmonize with the stitched present, users feel clarity and trust, which lifts performance in safety-critical environments. For time travel narratives, the moral is playful and serious. Even without machines, we already live a slight distance behind the universe, and we leap that gap with guesses that mostly work. Any external manipulation of time will have to pass through brains that edit moments before admitting them, which means human factors are not an afterthought. They are the gate through which all temporal engineering must pass. 76. Altered states compress or expand subjective duration without moving a second. Reports from meditation retreats, sensory deprivation sessions, and carefully monitored clinical settings show that the felt passage of time can slow to a crawl or bloom into expansive clarity while wall clocks proceed normally. Brain imaging ties these shifts to changes in the balance between networks that track internal signals and networks that model the outside world, which suggests that time as lived is negotiated between body and environment. When internal cues dominate, moments stretch because the mind processes more layers of interoception per unit of external time. When external tasks capture attention with fast feedback, moments shrink because prediction outruns reflection. This plasticity can be used to design recovery protocols and creative workflows. Short controlled intervals of reduced sensory load grant the nervous system a chance to unjam its timing and return to work with renewed precision. Conversely, curated bursts of high-tempo interaction can accelerate skill acquisition by packing dense error signals into a compact span. The choice of which mode to cultivate depends on the goal, since the same hour can be shaped into deep rest or into concentrated practice by tuning stimulus and expectation. Safety matters when exploring altered timing. Extreme deprivation raises anxiety in some temperaments, and intoxicants can derail the very networks one hopes to train. Reliable benefits arrive from methods that respect physiology, such as breath pacing, light-based entrainment, and guided attention, where a teacher or device coaches the transition gently. The point is not to escape time, but to learn how subjective pacing can be aligned with meaningful work and humane rest. As culture recognizes that duration can be engineered from the inside, institutions from schools to clinics can schedule by experience as well as by clocks. Meetings that would normally sprawl can be compressed into crisp sprints, framed by deliberate pre-focus. Recovery that would normally be skipped can be honored with brief rituals that lengthen felt time sufficiently to reset stress responses. Mastery of internal tempo is not time travel in physics, yet it gives people the first taste of agency over their own timeline. 77. Memory disorders reveal that temporal order is a construct. Patients with damage to regions that index events in sequence often recall details, yet cannot place them on a coherent line, which shows that chronology is actively built rather than passively given. Even healthy brains can be tricked into misordering flashes and taps when stimuli land near the limits of integration, which proves that the sense of before and after is an inference that usually works because the world is kind. When the inference fails, the present phrase and the past becomes a cabinet with drawers that no longer stay in place. Understanding this construction guides both therapy and design. Tools that tag events with redundant cues such as location, emotion, and social context help memory find multiple paths to the right drawer. Timelines in software that allow flexible grouping and replay help people reorganize life after injury by giving the mind external scaffolds to rebuild order. These aids are extensions of the brain's own strategy, which knits episodes together with labels and landmarks, rather than with absolute time. For science, the disorders become experiments. Nature runs to expose the parts list. By comparing which deficits follow which lesions, researchers map the circuitry that binds events into stories. The map, in turn, inspires algorithms that can clean surveillance footage or transaction logs by learning which patterns of error are typical when order is inferred from noisy streams. The flow of time becomes a problem in signal processing that brains and machines solve every waking moment. The ethical lesson is tenderness. If temporal order is a work product, then blame for confusion is misplaced. Designers and caregivers who accept this build systems that forgive slips and that offer gentle prompts rather than punishments. A society that treats chronology as collaboration between mind and world will be kinder and more effective long before physics grants any grander control. 78. Quantum consciousness proposals test non-linear sampling of moments. Speculations that microprocesses in neurons harness quantum coherence are controversial, yet valuable because they force testable questions about whether awareness samples time in a strictly linear way. If tiny coherent states contribute to experience, then patterns of interference could bias which micro-moments are admitted into the stream of awareness and which are discarded, a selection that might show up as subtle deviations in reaction timing under very cold or very controlled biochemical conditions. Experiments capable of deciding this are hard because warm, wet tissue decoheres rapidly, and because human timing is noisy even under perfect lab control. Still, work on cryopreserved tissue and on synthetic circuits built to mimic ion channel dynamics hints at regimes where coherence can last long enough to matter for the first step of signal transduction. Parallel work in cognitive timing uses tasks with millisecond precision to look for statistical fingerprints that would betray interference like structure in perception. The likely outcome is that brains remain classical at the level of integrated function while flirting with quantum effects only at threshold events. That outcome is itself a guide. It says that the route to reshaping subjective time is through networks and prediction rather than through exotic quantum tricks. Should a tiny effect be confirmed, it would add spice rather than overturning the main meal, since the macroscopic arrow would still be written by metabolism, learning, and attention. Either way, the inquiry professionalizes conversations that otherwise drift into mysticism. By asking hard questions, building careful apparatus, and accepting unglamorous answers, the field strengthens our grasp on how living systems bind moments into meaning. That discipline is the same discipline any future time technology will require. 79. Dreamtime frequently abandons the rules of external clocks. During rapid eye movement stages, the brain synthesizes narratives that can encompass long journeys and complex plots within minutes of wall time, or that stretch a single glance into an endless fall. This elasticity comes from the loosened coupling between sensory input and internal simulation, as the generative networks run largely on their own dynamics. Without the anchor of steady stimuli, the brain's models write time with whatever ink best suits the imagined scene, which teaches that orderly duration is a negotiated treaty, not a law. Harnessing this freedom is the aim of lucid dreaming and targeted memory reactivation, where cues introduced just before sleep or during light phases influence dream content. Early studies show that skills rehearsed in lucid dreams can improve waking performance, and that emotional material can be reframed when the dreamer knows they are dreaming. These are first steps toward a hygiene of imagination, where night hours become less random and more restorative. Care is needed because dream content can amplify fear when cues are clumsy, and because poor sleep erodes the very consolidation processes one hopes to guide. The art is subtle cueing, consistent bedtime routines, and respect for individual variation in sleep architecture. Technology can help with gentle audio signatures and wearable tracked rhythms, yet the core remains patient practice. From the perspective of time engineering, dreams are workshops where minds learn to bend narrative duration safely. A culture that honors those workshops will raise people comfortable with plastic time in the only place where plasticity is already granted. Such comfort will be essential if later devices ask users to trust experiences that depart from ordinary pacing. 80. Computation can simulate days inside minutes if run at extreme speeds. A program that models a world can advance its internal clock more quickly than wall time, if hardware allows, which means that agents inside the simulation experience a thickened, now compared with their operators. Even without sentient agents, the same principle gives designers the ability to rehearse weather, markets, or materials aging in compressed schedules. The trick is not only raw speed, but also fidelity. Since mistakes made in the model are mistakes made in the future, one thinks they foresee. Hardware progress points to accelerators and specialized architectures that trade generality for speed on specific workloads. When combined with better generative models for uncertain inputs, the result is not prophecy, but a cone of plausible futures computed fast enough that human teams can iterate policy and design before reality locks a choice. This is practical temporal leverage because the cadence of decision-making is no longer bound to the cadence of events. Governance must keep pace because rapid exploration can become reckless if results are mistaken for certainties, or if the ability to simulate is hoarded by a few actors. Open benchmarks, transparent uncertainty reporting, and audits that record which simulated histories informed which decisions create accountability in a landscape where time can be bought in bulk through silicon. The philosophical echo is striking. Long before tunnels appear, societies can live in futures that are calculated rather than traveled to. The benefits are real if humility accompanies speed. The cost of hubris is policy that outruns truth and crashes into reality's guardrails. 81. Simulated civilizations may experience time as a software choice. If conscious agents can exist in computed environments, then their lived duration depends on how often the scheduler allocates cycles to their processes. A pause at the host level becomes a time skip for them, and a budget increase becomes longer afternoons. From their perspective, the constants of nature are whatever the kernel declares, and the arrow is whatever the saving and loading policy enforces. This is a radical reframing of time as resource allocation. Ethics becomes immediate because control over pacing is control over life. Agreements about fair scheduling, about the right to continuity, and about consent for suspension are required if such worlds are to be more than toys. Technical safeguards must make sure that state is preserved faithfully and that transitions between rates do not corrupt memory, which are requirements that echo safety standards in aviation and medicine. For research, these worlds offer test beds where social dynamics, economics, and cognition can be explored across generations, packed into days. The danger is confusing model for reality and importing fragile conclusions into policy. A healthy culture of simulated science will publish limitations as prominently as findings, and will resist the allure of perfect control by embracing the mess that gives true systems their resilience. Temporal engineering in this context is gentle but profound. It is the stewardship of lived time as a parameter that can be dialed. The skills learned here will influence how we build interfaces for any later device that touches external duration, because empathy for experience will be baked into the design team. 82. If reality is computed, time complexity could be the real currency. Every algorithm has a cost measured in steps and memory. If the universe itself runs on computation, then laws that look like conservation of energy might be reflections of deeper constraints on how many steps can occur in a region per unit of cosmic time. This perspective pulls attention toward limits, like the Margolis Levitin bound on how fast systems can evolve given energy, and toward the Bekenstein bound on how much information fits within a boundary. Engineers already live by such limits when designing processors and networks, power budgets, cap clock speeds, and heat removal caps, density, which forces architects to find efficiency through parallelism, locality, and clever data movement. If nature shares the same pressures, then future breakthroughs in physics may rhyme with breakthroughs in computer architecture, and devices that manage time will do so by distributing work and reducing wasted cycles rather than by brute forcing against immutable ceilings. The currency metaphor clarifies policy. Groups that squander time complexity on vanity computations will fall behind groups that spend it on error correction, prediction, and resilience. Education that teaches algorithmic thinking becomes education that teaches how to move gracefully within the clockwork of the world, a practical philosophy of time that pays dividends whether or not the substrate turns out to be code. For narrative, the romance shifts from machines with levers to systems with schedulers. Control panels will display cues, latencies, and throughput rather than glowing rings, and mastery will look like graceful orchestration of processes across scales so that every tick is spent where it lifts the future the most. 83. Reversible computing hints at physics where time costs can be refunded. Ordinary computation throws away bits during erasure, which heats the environment and writes an irreducible arrow into the process. Reversible computing designs logic so that operations can be run backward to recover inputs from outputs, which in principle allows computation with arbitrarily low energy if run slowly and carefully. In that limit, the time cost can be traded against heat, which is a literal exchange rate between duration and dissipation. Building useful reversible machines is difficult because noise and error accumulate, and because practical algorithms often rely on erasure for simplicity. Yet progress in adiabatic logic, ballistic switching, and algorithmic transforms shows that chunks of real workloads can be recast in forms that approach reversibility. Quantum computation forces the issue because unitary evolution is reversible by construction, which explains why error correction is central and why measurement is the expensive step. For time engineering, the lesson is that some arrows in technology are habits rather than necessities. Where reversibility can be restored, loss can be reduced, and sequences can be rewound within subsystems to undo mistakes without global resets. This does not violate causality. It exploits freedom left by physics to avoid paying heat for steps that do not need erasure. A culture that learns to think in reversible terms will build machines that feel different. Buttons will have unpress functions designed in from the start. Pipelines will expose reversible segments where audits can trace errors back without relying on logs alone. The value of a second will rise because fewer seconds will be wasted as heat. 84. Landauer limits tie information erasure to heat and time. Erasing a bit in a system at finite temperature demands a minimum dissipation, which anchors the floor of energy per logical reset. That cost translates into delays, because real devices must channel the heat away safely, which means that faster erasure requires better cooling and more power. Computational time is therefore married to thermodynamic time in a way that no clever coding can annul. Only respect. Designers respond by batching erasures, by caching intermediate results to reduce resets, and by using error-correcting codes that allow many small reversible steps before a necessary irreversible checkpoint. These tricks rearrange when and where heat is paid, which in turn spreads the temporal profile of a computation so that peaks do not choke performance. The visual is a smoother curve of power and a steadier hum of ticks. At system scale, the limits drive placement. Data centers move closer to cold climates or to renewable power sources that can absorb peaks without cost spikes. On-device heterogeneous architectures schedule hot tasks in bursts and slide cool tasks into the gaps. Users experience longer battery life and fewer thermal throttles, which feels like time gained, though the equations simply moved costs into places where they hurt less. Understanding the limit also inoculates against wishful marketing. Claims of free lunch in processing can be checked against the ledger of erasures and heat. If the numbers do not close, the proposal is romance, not engineering. This honesty is the same honesty needed when confronting grander dreams about traveling in time. 85. Error. Correcting codes in quantum gravity could preserve temporal coherence. Ideas that connect holography with error correction suggest that space-time itself may behave like a code that protects interior information from small disturbances on the boundary. If so, the durability of histories in a region depends on code distance and on how well the boundary dynamics maintain the checks and balances that define the code. Temporal coherence becomes a property that can be strengthened by improving how information is woven across surfaces. This perspective reframes experiments. Instead of directly probing unreachable interiors, one tests how robust correlations are under controlled noise on the edges and infers code parameters from the results. Laboratory analogs in cold atoms and superconducting circuits can implement small toy versions, where bulk-like behavior emerges from encoded boundaries and where fault injection maps the resilience of the emergent time. The engineering spin is powerful. If codes build space and time, then codes can stabilize devices against drift in their own internal clocks. Networks can treat synchronization as a decoding problem, where each node repairs its local time by consulting redundant parity held by neighbors. The approach scales from chips to satellites if the math is right, and the protocols are simple enough to survive real-world conditions. By turning geometry into coding, temporal control moves from fantasy into software and signal processing. The wonders remain, yet the knobs become familiar ones, labeled parity, syndrome, and threshold. Which is good news because those knobs already sit on many benches. 86. Entropy can be reinterpreted as missing information about microstates. When a gas spreads, or when a memory fades, what grows is the ignorance about exactly which arrangement the system occupies within the large set compatible with the few facts one tracks. This reinterpretation ties the arrow of time to the bookkeeping of knowledge and lets sensors and records act as machines that push back against disorder by narrowing possibilities. Every measurement is a small reversal of ignorance paid for by energy and careful design. Practical implications flow into any field that manages flows of data. Archival systems that preserve provenance maintain low entropy stories because they keep fine-grained links between cause and effect. Scientific protocols that pre-register hypotheses and record null results reduce the entropy of literature by preventing the loss of negative findings. In both cases, time is clarified because one can reconstruct sequences without gaps that invite myth. In technology, the link shapes caching and compression. Predictive caches lower effective entropy by guessing future requests and staging data before users ask which shortens felt time, even when bandwidth is unchanged. Compression algorithms embed models of expected patterns so that data streams become smaller by agreeing in advance on which possibilities are likely. The shared model is a time machine of sorts because it lets sender and receiver meet halfway between past and next. By adopting entropy as missing information, organizations discover that time management is knowledge management. The fastest path through a project is often the path that removes uncertainty early with decisive measurements, rather than the path that adds more effort late. That habit builds timelines that feel shorter without violating any physics. 87. Maxwell-Demon thought experiments are tamed by accounting for memory. The imp that sorts fast and slow molecules to extract work from a single heat bath appears to defeat the second law, until one tracks the costs of measuring, storing, and erasing the records needed to run the trick. When the full ledger is kept, the demon pays back the free work with interest, and the law stands. This victory of careful accounting over clever paradox is a template for debunking many seductive schemes that promise temporal loopholes. Laboratory demons exist in miniature, where feedback control harvests work from fluctuations in colloids or single-electron devices. Their yields match predictions when information costs are included, which confirms that nature admits local order bought with knowledge while protecting the global arrow. These devices are not disappointments. They are blueprints for sensors and engines that sip energy with finesse rather than gulps. The cultural lesson is ruthless honesty. If a proposal claims to rewind a process, one must ask where the records go and who pays for erasure. If a device claims to age more slowly, one must ask who subsidizes the synchronization later. Each honest answer replaces mystery with design and turns miracles into services with price tags. Time travel talk matures under this lens. Dreams become projects when they survive the demon's audit. Projects deserve investment when their ledgers balance in test rigs. The demon is a teacher of budgets rather than a gatekeeper of impossibility. 88. Feedback control can locally push entropy downward for a while. Controllers that watch a system and apply small nudges based on measured deviations can hold it near unlikely states for extended periods. Refrigerators do this for temperature. Phase-locked loops do this for timing. And biological homeostasis does this for everything from glucose to posture. These are islands of maintained order in seas that would otherwise drift, which means local arrows can be written by design so long as power and attention are sustained. The reach of feedback grows as sensors sharpen and actuators miniaturize. Microfluidic labs hold delicate chemical states just shy of spontaneous reaction to study rare pathways. Quantum feedback stabilizes fragile superpositions long enough to perform logic that would decohere if left unguarded. In each case, the controller replaces the blind push of chance with a guided stroll through state space, which feels like time bent to will. Limits remain because the controller itself must be cooled, powered, and monitored, which moves the entropy burden rather than erasing it. Stability margins and delays can also turn helpers into hazards when loops oscillate or run away. The art is in tuning gain and phase to avoid excitement, and in designing graceful failure that releases systems safely when power or attention falters. Feedback is a gentle cousin of time travel because it keeps parts of the world near a snapshot that would otherwise fade. The insight scales. Cities can hold social indicators near healthy ranges with policy feedback. Ecosystems can be shepherded with measured interventions. The same math guides all of it and builds the habit of steering without hubris. 89. Biological systems exploit information to beat thermal noise in time. Cells harvest gradients and memories of recent conditions to bias reactions so that rare beneficial events happen more often than chance would allow. Enzymes are shaped to lower barriers in ways tuned by evolutionary history, which is a database of what worked across eons. Circadian clocks anticipate dawn rather than merely reacting and thereby align metabolism with opportunities. This is time management written in proteins and ions. Synthetic biology extends this craft by wiring feedback into gene circuits so that microbes can track moving averages of toxins or nutrients and act before levels cross dangerous thresholds. Tissue engineering uses pulsed signals to guide growth along developmental timelines, rather than forcing constant exposure, which reduces stress and improves outcomes. In each example, information buys order, and order buys time to adapt. At the organism level, communities build culture to store long memories that outlive individuals. Rituals, calendars, and architecture embed timing wisdom into daily life so that harvests are reaped and stored before weather turns. These social clocks are not mere decoration. They are survival algorithms that convert knowledge into resilience against the arrow that would otherwise sweep unprepared groups aside. The bridge to physics is sturdy. If life can write better stories by learning, then machines can too. Timelines for projects, supply chains, and health systems improve most when the right data arrives early enough to matter, and when decisions are rehearsed in advance. Information is not only power, it is time. 90. Life may require an arrow of time that aligns with increasing complexity. The rise of order from chemistry to cells to minds suggests that environments where entropy increases gently while energy flows steadily are the habitats where complexity thrives. If the arrow were neutral or reversed on average, repair and learning might not accumulate. Instead, an incremental drift toward disorder, paired with continuous input, seems to give systems room to build scaffolds against decay. This pairing could be the quiet reason why our cosmos hosts observers who ask about time. Evidence comes from non-equilibrium thermodynamics, where driven systems self-organize into structures that channel energy more effectively, from ecosystems that evolve webs of cooperation and competition, and from brains that turn sensory streams into models that compress the world. Each case relies on a background push toward mixing that never quite overwhelms the capacity to carve islands of order. The dance works because the arrow is strong enough to make room for novelty, but not so strong that novelty is crushed. If this is right, then attempts to erase the arrow locally must be undertaken with care, because the same force that might grant respite could also stall the very processes that give meaning to respite. Laboratories that slow time for tissues to heal must ensure that signaling pathways still progress. Societies that seek stability must allow enough turbulence to renew ideas. Balance is not a slogan. It is a physical requirement for growth. For the dream of traveling to futures or pasts, the implication is poignant. Choose goals that do not sabotage the conditions that make life and learning possible. The best technologies will grant more time within the same universe that nurtures complexity rather than ripping travelers into sterile eras. Mastery will look like gardening the arrow, not defying it. 91. Could the Planck length and Planck time define the boundary of all possible change? Physicists combine fundamental constants to form a length so small and a time so brief that below them the familiar language of fields and waves likely breaks and something more granular takes over. If those scales are not only convenient markers, but true boundaries, then every process in nature is assembled from steps that cannot be subdivided, which makes evolution a ladder rather than a slide. That turns many smooth curves, in theory, into long exposure photos of clicks we cannot yet resolve, and it suggests that precision will meet a floor set by reality rather than by engineering. The boundary would tame infinities that plague naive models by refusing to honor distances and durations below its thresholds, which naturally regularizes calculations without a dozen patches. It also recasts questions about causality, because if events must be separated by at least a tick, then inference about who influenced whom must respect that cadence. In practice, this builds a buffer against paradox, because you cannot demand reactions faster than the universe permits. Evidence will be indirect at first. Astronomical paths provide billions of light years for tiny irregularities to accumulate into measurable phase errors, and ultra-stable laboratory interferometers provide millions of steady seconds in which a hum of fundamental jitter might appear if one listens well enough. The absence of such signals so far pushes discreteness deeper or forces a subtler hiding place. But patient improvements keep the search honest. If the boundary is confirmed, it gives builders new tools. Devices can lock onto the base tick and reject wander that cannot share it. Networks can synchronize to a scaffold that outlives any local oscillator. Education can teach intuition using staircases rather than rivers, so that the next generation sees controls and schedules as sequences of slots that can be allocated and braided, a mindset very close to what any practical time machine will require. 92. Is time travel possible only in universes with specific geometric curvature. General relativity grants many geometries, but not all of them host the same repertoire of paths and loops. Some require rotation or special kinds of stress to curl time into return routes, while others keep time stubbornly straight, no matter how matter is arranged. If this dependence is fundamental, then the question shifts from how to build a machine to where to place it, because only under certain curvatures can the ingredients combine into anything beyond forward flow. Observational cosmology already suggests that our large-scale curvature is close to flat, and that accelerated expansion will make it flatter over time, which quietly pushes grand temporal gymnastics toward unlikely corners, such as near compact objects or in transient regions during extreme events. The universe may permit exotic routes, but may do so stingily, which forces pragmatists to search for marginal gains rather than for shortcuts that cut centuries. A curvature requirement also filters science fiction from engineering. A civilization would need not only mastery of materials and energy, but mastery of astrophysical positioning, perhaps building stations in safe orbits around specific black holes that are friendly enough to allow approach, yet strong enough to offer the required twist. The logistics of supplying and governing such outposts would rival the device itself and would define new forms of law and diplomacy. This constraint is not bad news. It converts the dream into a surveying project that catalogs friendly geometries instead of a wish for a universal wand. Step by step, survey by survey, a map of feasible temporal neighborhoods would emerge, and the first working systems would likely resemble observatories and refineries more than gateways in a city square. 93. Can advanced computation simulate an entire second in a fraction of time? A model with enough resolution can march its internal clock much faster than the wall clock, producing many steps of evolution before the outside observer finishes a sip of tea. This grants planners and researchers a way to test actions and reactions across dense timelines that would otherwise require days or years to unfold. The catch is fidelity, because a fast model that misses key couplings returns confidence without truth and can tempt decision-makers into errors that only the real world has the heart to correct. The path forward blends specialized chips, compressed representations of physics or society, and ensembles of runs that cover uncertainty rather than pretend to eliminate it. This turns prediction from fortune-telling into risk mapping, where the output is a field of scenarios with weights that update as new data lands. When done with discipline, agencies gain cycles of reflection in the narrow gaps that history allows, which is as close to bending time as a bureaucracy can get without breaking law. Ethics and access are as central as algorithms. If only a few actors can buy enough cycles to live many simulated lives within a single week, those actors gain a quiet advantage that can distort markets and politics. A culture of disclosure, third-party audits, and shared baselines can conserve fairness without spilling intellectual property, much as laboratories share reference materials while keeping proprietary methods. With maturity, fast seconds will reshape the cadence of design and governance. Teams will meet not to guess, but to compare branches already explored in software. Failures that once cost years will cost an afternoon. Yet wise leaders will remember that real seconds still hold the only verdict that counts, and will keep rights of humility in the loop, so that simulated courage does not outrun real courage. 94. Could time dilation explain certain unidentified aerial phenomena? Some reports describe motions and accelerations that would crush known materials and bodies if experienced in the usual frame, which invites the speculation that the objects are riding geometries where local time is stretched so that violent changes appear mild inside. If occupants dwell in slow time while observers watch from fast time, the apparent defiance of inertia softens to a mismatch in clocks rather than a violation of force. This is not a claim of truth, only a hypothesis that urges careful tests. Such a hypothesis demands data with timing integrity that rules out camera artifacts, rolling shutter confusion, and parallax illusions. Multi-sensor baselines with synchronized clocks can measure not only position, but local timestamps, and comparison across instruments can either crush the idea or nourish it with anomalies that survive honest scrutiny. Most candidates wilt under this light, which is a feature, not a bug. Strong claims deserve strong exposure. If any residue remains after instrument rigor, the remedy is to build calibrated chases and passive arrays that can triangulate while logging timing with atomic references. Platforms that measure gravitational gradients and magnetic fields add context about whether local geometry and fields are being manipulated. The bar is high, but reachable, if curiosity is matched by discipline. Even if no exotic dilation ever appears, the pursuit refines our ability to read the world without fooling ourselves. It trains teams to keep time as a scientific variable rather than as a byproduct of video. That training will pay dividends in every domain where milliseconds separate signal from story. 95. Can we manipulate quantum vacuum fluctuations to open micro-time portals? The vacuum seethes with transient pairs and brief ripples that average to calm over longer intervals. The idea is to shape that seething with cavities and squeezed states so that negative energy appears in controlled patches, then use those patches to prop open tiny corridors where the bookkeeping of proper time becomes strange for a blink. The theory says the patches are real but brief and bounded, which makes the dream a fight against inequalities that cap both depth and duration. Laboratories can already create regions where the energy density dips below the naive baseline, as measured by forces between plates and by noise in carefully prepared light fields. Scaling from microscopic forces to passages wide enough for signals is a climb that crosses many orders of magnitude, and instabilities loom if even a sliver of success is achieved, because the vacuum resists being bullied for long. The engineering response is to aim small. Use the shaped vacuum as a phase tool in interferometers, as a protective skin that cancels decoherence around fragile qubits, or as a timing shim that advances or delays events by margins useful for sensing and communication, rather than for voyages. Each win teaches how to stack and synchronize many small effects into one macroscopic service. Someday the stack may grow tall enough to resemble a portal for photons, then for larger excitations. Yet each rung will be paid for with painstaking control and ruthless error budgets. Romance is allowed in the proposal stage, but only discipline survives the build. 96. Is the cosmic speed limit just a safeguard against paradoxes? The universal limit prevents observers from arranging signals that circle back and scramble cause, which makes it feel like a constitutional law written to defend consistency. While the limit arises naturally from the symmetries of space-time, the result is the same as if a committee cared about keeping stories straight. Try to exceed the limit, and the algebra pushes back with imaginary times and broken invariants that warn you long before a machine shop has a chance to sin. Experiments that keep checking the limit serve as auditors of causality. High-energy photons from distant flares arrive without energy-dependent lag large enough to suggest a tilted playing field. Colliders show that particles respect the transformations that enforce the limit even when pushed into regimes where tiny deviations would show. Navigation satellites would fail within hours if the mathematics were slightly wrong, yet pilots land and freight arrives. Treating the limit as a safeguard changes design culture. One stops hunting for raw speed tricks and starts hunting for geometry, correlation, and code that live comfortably within the cone. Wormholes, if they exist, never let a signal sprint outside the cone locally. Entanglement, as demonstrated, never lets a message hitch a ride. The playground is still enormous, yet the fence is respected. A society that accepts the fence thrives by mastery rather than by rebellion. The work shifts from brute force to subtle orchestration, from heroics to craft. Time travel, if it ever arrives, will be the art of composing constraints into passage, not the thrill of breaking a speed limit sign. 97. Can we manipulate quantum vacuum fluctuations to open micro-time portals? The restless ground state of fields is a sea of jitter that cannot be stilled entirely, yet small regions can be quieted or inverted for brief spans. The hope is that by building cavities and sequences of squeezed light, one can carve pockets that nudge the local geometry of time enough to create controlled advances and delays for fragile signals. This is less a door than a lens that focuses or defocuses the flow, and it targets photons and phonons before anything with rest mass. Practical progress would be incremental. A pocket that advances a light pulse by a small fraction of its duration without distorting its information is already a communications asset, while a pocket that delays with low noise is a buffer for synchronization. String many pockets and modulate them in carefully choreographed phases, and the envelope begins to behave like a programmable timeline for waves inside. Instabilities limit ambition. The same configurations that produce helpful negative energy also invite violence elsewhere, and the global accounting enforced by quantum inequalities ensures you cannot linger in luxury for long. As a result, power must be pulsed and geometry must be adjusted on the fly to spread stress. The craft looks like juggling bright knives with slow hands and deep caution. The endpoint is unknown, but along the way the devices refine clocks, stabilize qubits, and sharpen interferometers. Even if a true portal never arrives, the journey arms society with instruments that make time a partner rather than a mere parameter. 98. If time had direction before the hot beginning, where did it point? If our observable era emerged from a prior phase, then the arrow we experience might descend from conditions that predated the plasma and nuclei and atoms that later filled the sky. The question becomes whether the previous era handed us a low-entropy seed or whether the arrow was reset by violent dynamics that erased earlier memory. Evidence hides in the largest scale correlations and in relic backgrounds so faint that present instruments barely whisper their names. Models diverge. Some bounces sow the arrow through the neck by mapping late times of a contracting stage into early times of our expansion, while others erase enough detail that the arrow is born anew. The difference matters because one predicts echoes we might find with patience, while the other predicts a silence we must learn to love. Observations of polarization, spectral distortions, and gravitational wave backgrounds are the tests that can decide. The answer will influence philosophy as much as equations. If the arrow is heirloom, our time is a chapter in a long family saga where cause and effect have been practicing for ages. If the arrow is newborn, our time is a fresh draft with fewer constraints and possibly more opportunities for novelty than a long memorized script would allow. Either outcome is rich, Engineers should care, because a cosmos with inherited direction might also inherit subtle biases that good instruments can exploit, while a cosmos with reset direction demands tools that can right order without relying on buried scaffolds. In both cases, humility is the correct tempo, because the beginning of beginnings is not obliged to be simple. 99. Could black holes be cosmic recyclers of time itself? Matter and information fall inward. Radiation flows outward over unimaginable spans, and deep inside, the equations offer the possibility of bounces or tunnels that send content elsewhere or elsewhen in ways that maintain consistency through global accounting. In this picture, black holes are not garbage disposals, but processing plants, where sequences are shredded into scrambled codes that later reassemble as correlations across the sky. The notion is audacious but fits the refusal of physics to delete information outright. Evidence remains circumstantial. Page curve arguments and holographic dualities suggest that evaporation is not blind, while observations of near-horizon, light patterns, and ring-downs confirm that horizons behave according to clean metrics that do not yet hint at drama. Laboratory analogs mirror some aspects and show how horizons can be emergent, which encourages more controlled studies, even if they cannot settle cosmic matters on their own. If recycling holds, then time in the universe is threaded around these processors. Astronomers become archivists who decode where and when the outgoing quanta point back to, and the sky becomes a library of returned information written in a script we are just learning to read. That reimagines the entire enterprise of observation as a dialogue with ancient collapses, which is a romance worth years of instrumentation. For technology, the metaphor inspires designs that never throw away state, but instead shuffle and encode it for later use. Time machines, built by such minds, will be coders first and travelers second, and their success will rest on whether the code runs cleanly on the fabric of reality. 100. Are we misinterpreting time as linear when it is actually fractal? Natural systems show structures that repeat with variation across scales, and some theorists have explored whether temporal correlations might exhibit similar self-similarity. If processes carry memory that spans orders of magnitude, then statistics that assume neat separation of timescales can be badly fooled, making straight lines on familiar plots where bends and loops truly reside. A fractal time would not erase order, but would hide it inside patterns that do not simplify when you zoom. Tests look for power law spectra in fluctuations, long-tail memory in materials and markets, and cross-scale couplings in turbulence and neural dynamics. Many fields already report such signatures, though disentangling genuine fractality from mixtures of ordinary processes remains hard. The more we look, the more we find systems that refuse clean exponential relaxation and insist on messy, scale-free sagas. If time is fractal in behavior, if not in ontology, design must adapt. Controllers that assume single characteristic times fail, while controllers that learn distributions and adapt gains across bands thrive. Schedulers that expect tasks to finish in tidy windows disappoint users, while sizers that budget slack for rare long events keep teams happy. The world rewards those who respect fat tails. For time travel stories, the lesson is about humility in prediction. Even without portals, we are poor at forecasting because the past weighs in with echoes of many ages. The smart response is to build resilient systems that bend and recover rather than brittle systems that shatter when history stutters. 101. Could the perception of now travel at a measurable velocity? The brain integrates signals over windows that take time, and those windows must be shifted and aligned across sensory modalities to form a unified moment. If the alignment is dynamic, then the boundary of now could move through cortical maps with affinity speed, much like a wave that declares this is present across regions in sequence rather than everywhere at once. Subtle experiments with high-density recordings might catch this sweep in action. Evidence would be patterns in phase relationships that propagate across cortex as tasks demand different integration horizons. For fast decisions, the sweep would sharpen and speed up. For reflective tasks, it would slow and widen. Training and fatigue would tune the velocity, and disorders would reveal failures of alignment that feel like time fragmentation to the patient. The now would become a measurable object rather than a mystical word. If the sweep exists, interfaces can cooperate by presenting cues in patterns that match its pace, so fewer corrections are needed and fewer mistakes are made. Pilots, surgeons, and traders would feel a reduction in cognitive friction when tools respect the brain's own metronome. Entertainment would borrow the tricks to create experiences that feel crisp without stress. Philosophically, this does not diminish wonder. It grounds the slippery concept of present in a biological rhythm that can be measured, trained, and respected. The art of living then includes tuning one's now, which is a skill available to anyone with patience and practice. 102. If time is relative, could morality be as well? When physics stripped absolutes from space and time, it left culture free to imagine that values are just as pliable, yet the analogy breaks easily. Relativity builds invariant structure beneath the differing accounts of observers, while moral relativism often abandons shared anchors. The interesting question is whether an invariant moral core exists that plays the role of a light cone for action, defining boundaries of harm and consent that do not change with speed or altitude. Technological futures with time dilation and asynchronous lives will stress ethics in new ways. A traveler who returns decades later will find debts and promises aged beyond recognition. A worker who spends months in a high-gravity lab may claim different rights and obligations than a colleague who stayed under gentle skies. Law will need invariance for identity, agency, and responsibility that survive skewed clocks. A practical approach is to define conserved quantities for social systems, such as preserved consent trails, auditable histories of commitments, and shared protocols for reconciliation when timelines diverge. These become the moral equivalents of invariance, objects that remain trustworthy despite distortion. Cryptography and distributed ledgers can help, but only if culture agrees on what is sacred about persons and promises. Engineering time without engineering ethics is reckless. The wise blueprint puts moral invariance in the foundation so that the beautiful distortions above do not crack the house. That blueprint starts now, long before anyone builds stations near compact objects. 103. What would a civilization that mastered time look like to us? From our vantage, they would appear patient and sudden at once. Projects would unfold in places where time runs slowly for them and quickly for us, so bursts of art and technology would arrive in leaps that seem miraculous while their creators experienced long, thoughtful seasons. They would favor archives that survive epochs and channels that cross ages, and they would seem absent until one learns to read their calendars. Economics under such mastery would decouple investment horizons from human memory. Trusts could sit in slow zones compounding value, while fast zones innovate and spend. Then reconciliation steps would return gains without shocking either side. Law would codify temporal jurisdictions, and culture would accept that age and rank are world-line properties rather than simple dates. Their architecture would exploit gradients. Universities would perch where research borrows centuries at little subjective cost, while hospitals would choose places that dilate recovery. Arts would play with rhythm beyond human reach, composing works whose movements require years of outside listening for minutes of inside performance. To us, the pattern would feel alien until we save enough seconds to hear it. Their diplomacy with younger species would be conservative. Gifts that depend on temporal infrastructure would be withheld until the student can maintain the gradient without harm. Lessons would arrive as clocks and codes rather than as engines and doors, because mastery begins at measurement and memory. We might already be inside such a lesson without recognizing the teacher. 104. Can we send information backward without sending matter? The dream threads through quantum tricks that correlate outcomes across time while refusing to carry messages locally, through post-selection that sculpts history after the fact, and through exotic geometries that pinch world lines together without letting mass outrun light. Every route so far hits the wall built by no signaling or by consistency principles that prune paradox. Yet the edge cases hint that boundary conditions can influence what histories survive while staying shy of contradiction. A practical formulation is to design protocols where choices made later determine which earlier records become meaningful, turning yesterday's noise into today's signal once a key is issued. This is not messaging to the past, but it feels close because meanings change retroactively when the key arrives. Distributed systems already exploit this through commit and reveal schemes that protect integrity while enabling surprising coordination. Further progress would build laboratories where entire experiments are designed as global objects across time. Weak measurements, delayed choices, and clever encodings would be combined so that future settings determine the printable version of past traces, while forbidding any useful prediction before the reveal. Such systems could serve cryptography, secure auctions, and fair randomness in a world suspicious of manipulation. If this is the only kind of backward influence that nature allows, it is still valuable. It grants a vocabulary for coordination that saves face for causality, while delivering magic to users who only see that choices made tomorrow made sense of yesterday. 105. Could entangled particles be future and past versions of each other? Some interpretations picture entangled pairs as one object stretched across time as well as space, with measurement knitting the halves into a single story that spans before and after. In this view, what looks like spooky action at a distance is a bookkeeping choice about where to cut the story, rather than a signal racing across a gap. The mathematics is unchanged, but the narrative feels less like a cheat and more like a reminder that time slices are human conveniences. Testing such a picture means little in the lab because predictions match the standard account, yet the picture helps engineers think about protocols. When designing networks that swap entanglement across nodes and times, it becomes natural to store half of a pair and treat later operations as completing a figure begun earlier. This shifts mental models from messages to sculptures and often reveals simpler paths to the same goal. Security and error correction benefit from the sculpture view. One can treat losses and noise as chips and cracks in a statue and plan restorations that respect the global shape rather than patching surfaces blindly. Thresholds for code success become symmetry conditions for the whole story, and checks can be placed where they guard the maximum amount of history. If entanglement is a bridge across moments, rather than only across locations, then travel in time begins with the courage to design entire experiments as wholes. We will not walk across the bridge with bodies, but we will learn to move meaning across it with grace, which is often the more powerful act. 106. Banking across relativistic zones would force new fairness rules for time. Finance relies on shared calendars and synchronized clocks, yet relativistic environments fracture that foundation by creating lawful differences in elapsed time between parties to a contract. Interest compounding, settlement deadlines, and default windows all presume a single river of seconds, which breaks when one counterparty lives closer to deep gravity or travels at sustained high speed. A loan that accrues for 10 external years while the borrower experiences 5 subjective years produces an ethical and legal mismatch that classical formulas never contemplated. The ledger might be correct, yet the lived burden diverges from the intention behind the rate. Designing justice under skewed time demands new invariants. Instead of dating obligations by local clocks, contracts would anchor to reference frames agreed in advance and audited by independent timing networks. Payment schedules would include conversion rules that translate obligations into the borrower's experienced duration, which preserves the spirit of fairness while keeping books consistent for regulators and investors. Auditable proofs of proper time accrued along each relevant world line become as important as proofs of funds. Infrastructure must evolve. Clearinghouses would run relativistic compliance engines that reconcile flows across habitats at different potentials, and exchanges would publish time-indexed yield curves that already price gravitational and kinematic spreads. Insurance would sell protection against timing basis risk the way it now covers currency and rate risk. Education for finance professionals would add space-time literacy so that disputes are solved with models rather than metaphors. Without these upgrades, markets would drift toward predation, where entities arbitrage unsuspecting communities through time gradients. With them, gradients become a shared utility. Pension funds might park reserves in slow zones to extend runway without squeezing beneficiaries, while fast zones host innovation that repays the patience. The point is alignment, so that time differences become a cooperative advantage rather than a hidden tax. 107. Legal systems would redefine age and consent when time runs unevenly. Age is the backbone of many rights and duties, from voting to contracts to family law. Yet age is currently counted by calendar time rather than by proper time. A traveler who experiences 6 years while the homeworld records 16 returns, both legally old and biologically young. A mismatch that invites exploitation and injustice. Guardianship, majority, and retirement cannot remain tied only to birthdays when biographies unfold along bent world lines. A humane regime would track dual ages. Civil status would use a reference clock for jurisdictional clarity, while personal capacity and consent would hinge on verified proper time along the person's own path. Medical and cognitive assessments would supplement the numbers so that discrete thresholds do not throttle nuanced lives. Records would include authenticated world-line logs that prevent fraud and allow third parties to rely on age-linked rights without guesswork. Family law must adapt. Parenthood and kinship traditionally presume close pacing through time, which unravels when one member spends long periods in slow habitats. Custody plans would schedule across mismatched calendars. Inheritance would consider both subjective and reference ages, and marital contracts would include provisions for long absences measured in radically different ticks. The goal is dignity for relationships that stretch across gradients, without collapsing under ambiguity. Criminal and civil liability would also shift. Statutes of limitation could toll based on the accused's proper time rather than only on reference calendars, and sentencing that uses time as punishment would consider how placement in faster or slower zones changes the felt duration. Justice must punish or protect in ways that track human experience, not only wall clocks. 108 sports records would need correction for altitude time advantages. Precision clocks already show that seconds pass slightly faster on mountains than at sea level, a difference that is tiny yet measurable. As performance margins shrink and money grows, even minute advantages become grounds for protest. A world that accepts gravitational time dilation as engineering fact cannot ignore it in arenas where fairness is the point. Courses at higher potentials would silently grant microseconds to athletes which accumulate into records that would not stand under uniform time. Leagues would respond with standardization. Timing systems would reference a common potential and publish corrected results alongside raw readings, much like wind adjustments in sprinting or altitude corrections for batting statistics. Venues would certify their gravitational profiles, and mobile events would include pre-announced correction rules so audiences and sponsors know what a record means. The debate would move from denial to calibration. Training would adapt. Teams might use slow time facilities to extend subjective practice while complying with season calendars, which amplifies disparities if not regulated. Governing bodies would likely cap the use of extreme gradients during active seasons or allocate equal access the way ice time or testing hours are capped in motorsport. The principle is simple. Competition should measure skill, not clever rentals of space-time. The culture of records would mature. A corrected world record honors the athlete while acknowledging physics, and historical marks can be retroactively annotated when venue profiles are known. Fans lose nothing by embracing honesty. The drama of human ability remains intact, and sports gain resilience against future scandals rooted not in drugs but in geometry. 109 art created in slow time would flood a fast world with output. An artist who spends 5 subjective years in a strong gravitational well, while the outside world races through decades, can return with a body of work that feels impossibly prolific to audiences who watched the calendar fly. A novelist could deliver a shelf of books in what the market perceives as a season. A composer could unveil a cycle worthy of a lifetime in a single festival. This is not cheating in the vulgar sense. It is craftsmanship placed on a different slope of time. Societies will need curators who can pace release without burning attention or crushing markets. Archives and staged premieres would spread output across reference years, and contract law would define fair recoupment periods for partners who cannot match the artist's productive tempo. Critics would learn to separate the delight of abundance from the fatigue of oversupply by guiding audiences through staggered discovery. Ethics arise within teams. Collaborators who remained in fast time might feel abandoned if the slow time artist returns with ideas that leapfrog shared plans. Credits and royalties would reflect both hours worked and risks borne, while acknowledging the asymmetry of clocks. New guild norms would evolve to keep trust intact across gradients, including shared worldline logs that track who contributed when. Culturally, slow time studios could become monasteries for art that demands patience, while fast time venues become playgrounds for live improvisation and audience co-creation. The two tempos would cross-pollinate, and art would gain a richer ecology not through magic, but through conscious stewardship of timing as a creative resource. 110. A relativistic monastery could produce centuries of scholarship in decades. Imagine an institution built near a compact but safe mass where faculty and students live with time stretched relative to the outside world. Inside, projects that require long reflection and careful replication thrive, free from the churn of fashion and grant cycles. Outside, society receives bursts of mature work that compresses generations of study into a decade of calendar time. The model balances contemplation with relevance by choosing a dilation factor that keeps conversation possible. Governance is the challenge. Admissions decide who gains access to the gift of extended attention, and accountability must ensure that isolation does not rot rigor. The monastery would publish world-line logs, pre-register agendas, and invite external auditors who visit at matched intervals, so standards do not drift. A fellowship would include mandatory rotations in fast time to maintain empathy with students, funders, and publics. The benefits extend beyond papers. Long-term instruments can be tended without the fatigue that ruins patience. Cultural memory can be maintained with fewer generational handoffs that normally erode context. Mentorship gains continuity because teachers see many cohorts without growing old as quickly in the reference world. A living chain of method forms, which is the heart of science when it is healthy. Risks remain. Power can pool in institutions that sit off the clock, and resentment can grow among those who cannot afford to leave the common tempo. Wise policy would treat relativistic study as a commons, funded widely and governed by rules that guaranteed diversity and open access to results. Scholarship earns legitimacy when its timing advantage serves everyone. 111. Messages to the past risk paradox, unless reality protects consistency. The first impulse is simple: send a warning and save a life, a fortune, or a planet. The second impulse is panic, because the very success of the warning could erase the need to send it, which erases the message, which restores the need, in a loop that never settles. Classical stories handle this with hand waves. Physics demands a mechanism that denies contradictions without breaking the rules. Two families of protection exist in theory. One insists that only self-consistent histories occur, which means any attempt to change the past becomes part of the past that already was, often through improbable coincidences that steer actions back into compatibility. The other diffuses contradiction by branching outcomes into separate realities, so that saving a life creates a world where the message was sent from a different history, not a rewrite of the sender's own. Engineering must assume protection exists, because the alternative is a broken universe. Protocols would therefore forbid messages that target events known to trigger contradictions, and would instead focus on information that archives or verifies rather than alters. Museums of the past become safe endpoints. Courts and finance build notarization channels that allow contested facts to be witnessed across time without inviting loops. The romance of rescue does not vanish, but it changes shape. A civilization that respects consistency will design institutions that reduce the need for retroactive fixes by building foresight and resilience. The best message to yesterday is a culture that rarely needs it. 112. The Novikov principle forbids self-inconsistent histories. This proposal states that the only solutions that ever occur in nature are those that are globally consistent, even if local choices feel free. A traveler who tries to kill their younger self finds that the gun jams or the path is blocked, or the attempt never quite aligns, not by magic, but by the structure of allowable histories. Freedom is constrained to moves that complete a loop rather than break it. Accepting this principle reshapes design. Time devices would include consistency analyzers that simulate candidate actions and allow only those with non-zero consistent solutions. User interfaces would present choices that look broad, yet are pruned by the mathematics, which is less oppressive than it sounds, because real life already prunes choices through physics and logistics. The novelty is the need for global checks rather than local feasibility alone. Ethically, the principle offers comfort. You cannot commit certain categories of atrocity through time because there is no self-consistent way to do so. It also offers frustration to heroes who wish to undo tragedies that formed them because their attempts will transmute into the very causes they hoped to erase. Stories become circles that must be written with care if they are to be elegant rather than cruel. Science gains a guide. Experiments that claim direct contradictions should be suspect, and designs that rely on changing fixed events should be scrapped early. Effort can focus on protocols that archive, anticipate, and harmonize rather than on schemes that hope to bully causality into retreat. 113. Self-fulfilling loops allow stable stories with circular causes. A note found in a lab saves a project. Years later, the scientist sends the same note back because that is how the rescue always happened. Nothing is created from nothing because the loop includes a physical process that stores and returns the message. Yet the origin feels mysterious because the content lacks an author in the usual sense. These are bootstrap tales, and physics permits them if consistency is maintained. Their value is not only narrative. Loops can act as memory across eras when ordinary archives fail. A culture could seed vital knowledge into its own past to guarantee continuity, provided the content does not create contradiction. Encryption and authentication would be essential so that malicious edits cannot hijack the loop. Auditors become historians who check that the looped data matches recorded outcomes. Limits protect sanity. Loops cannot contain arbitrarily complex blueprints without accumulating noise or provoking contradictions somewhere in their chain. Practical loops would therefore carry compact instructions or keys that unlock work done in the normal way rather than entire libraries. The loop acts as a spark, not as a furnace. Used wisely, self-fulfilling loops become instruments that remove chance from critical thresholds. Vaccines, fail-safes, and standards could be anchored by loops that guarantee arrival regardless of ordinary logistics. Used foolishly, they become tempting myths that excuse laziness. Culture must teach the difference. 114. Killing the ancestor becomes impossible if only consistent paths exist. The most famous paradox imagines a traveler erasing their own origin. Under consistency rules, the world will not allow final conditions that dissolve the premises. Attempts fail through mundane misfires or through improbable yet lawful barriers. The result is not a moral lecture, but a selection effect. Only histories that close their own loops survive to be lived. This has strategic implications. Security against temporal attack would lean on passive consistency rather than on active defense. Critical lineages would be surrounded by redundancy and by cultivated improbabilities that steer any interference into harmless outcomes. Think of layered contingencies and multiple independent paths that all produce the required ancestor, so that sabotage has nowhere to land without creating a contradiction. Psychology must adapt as well. People who feel haunted by mistakes may fantasize about deletion through time. A culture that understands consistency will guide them toward repair in the present and toward future-focused restitution, not toward impossible erasures. Responsibility remains, yet despair loses its glamour. Fiction will still explore tragedies in loops because drama loves impossible choices. Reality will whisper a gentler lesson. You cannot edit away the branch that holds you. You can only grow better branches from here. 115. Multiverse branching resolves contradiction by separating outcomes. When an event with multiple possible results occurs, one account holds that reality realizes all of them in parallel branches that cease to in practice. A decision to send a warning divides histories into those where the warning is sent and those where it is not. Paradox dissolves because each branch contains a single consistent narrative, and no traveler can leverage the difference to break causality without jumping between branches, which ordinary physics denies. Engineering in such a world shifts from control to selection. One can bias amplitudes toward branches. One prefers by arranging interference and decoherence carefully. Yet one cannot forbid disfavored branches entirely. The art becomes maximizing measure for outcomes that meet goals while respecting that some weight will always flow elsewhere. This is sober power, not wish-granting. Ethics must face the uncomfortable consequence that harms still occur in branches with non-zero weight. Consolation arrives in the recognition that our choices change the distribution, so care and courage still matter. Institutions would codify precaution where stakes are vast because even small weights carry moral cost when multiplied by consequence. Communication about branching requires literacy so the public does not confuse a technical picture with license for nihilism. Meaning survives because agency still changes futures within a branch and changes weights across all branches. The multiverse does not absolve. It enlarges responsibility. 116. Many worlds' interpretations place all outcomes into parallel realities. This view treats quantum evolution as smooth and unitary at all times, with apparent collapses arising from decoherence that hides alternative outcomes from each other. No dice are thrown at the fundamental level. The randomness we feel reflects our location within a branching structure that constantly refines as interactions spread. Time becomes the growth of a tree whose twigs never meet again at macroscopic scales. For technology, this perspective encourages strategies that avoid unnecessary measurement, thereby postponing branch separation inside devices so that coherent computation runs longer. Error correction becomes gardening that prunes interactions with the environment to keep the computational twig from fraying. Hardware roadmaps already follow this instinct, whether or not engineers swear allegiance to any interpretation. Culturally, many worlds supports a calm attitude toward uncertainty. It teaches that ignorance of outcomes is not always ignorance of reality, which reframes risk management and forecasting. We choose policies that work across likely branches, rather than betting everything on a single guess. The practice is robust planning rather than clairvoyance. For time travel talk, the message is boundary management. Once branches separate, navigation between them is not on the menu of ordinary physics. Ambition should aim at shaping the branch we inhabit and at maximizing the measure of humane futures, not at leaping sideways into a wishful version. 117. Decoherence explains why branches rarely meet again. Environmental interactions smear phase relationships between components of a quantum state so thoroughly that interference becomes practically impossible. The information that would be required to reverse the process has leaked into countless degrees of freedom, from air molecules to photons 2 vibrations in a bench. The tree of outcomes hardens as its twigs rub against the world, which is why macroscopic superpositions are laboratory miracles rather than daily events. This mechanism is not an extra law. It is the natural consequence of entanglement spreading through complex systems, and it sets the true cost of reversing time at scales larger than a few particles. To unwind decoherence, one must collect and process information distributed across a vast environment with precision beyond hope. The arrow emerges from sheer combinatorial explosion. Engineers can still play at the edges. Cryogenic temperatures, vacuum chambers, shielding, and clever encodings push the onset of decoherence outward, so that useful work is done before the tree branches irreversibly. The same tools make exquisite sensors because anything that disturbs coherence becomes a signal. Coherence is both a resource and a probe. The moral for temporal ambition is focus. Seek domains where coherence can be preserved long enough to matter, and accept that everyday mess is not a foe to be conquered, but a landscape to be mapped. Time bends only where coherence survives. 118. Quantum Darwinism selects robust facts that survive observation. When systems interact with large environments, certain states imprint themselves redundantly across many fragments of that environment, making them accessible to multiple observers without disturbance. Those states become classical facts because they are easy to read and hard to erase. The world we share is built from these survivors, while fragile alternatives vanish into inaccessible correlations. This process explains why we see tables and cats rather than delicate superpositions, and it grounds objectivity in redundancy rather than in fiat. Timing enters because the spread of imprints takes finite intervals, and the order in which fragments reach observers shapes consensus. Facts have growth curves. Designers can exploit the idea by engineering records that are deliberately redundant across independent channels, which raises trust and speeds agreement. Scientific instruments already do this when they log to multiple media and broadcast to multiple teams. Financial systems mirror the strategy with distributed ledgers. Redundancy is not waste. It is how reality chooses winners. For temporal engineering, the lesson is about leaving footprints. If you want a state of the world to persist, write it into many places quickly. If you want to explore exotic states, shield them from environmental gossip until you are ready to reveal them. Time favors gossip. Use that to your advantage. 119. Records and memories give the arrow its bite by fixing history. Entropy growth explains the bias toward disorder, yet the day-to-day force of time in human life comes from records that resist revision. Photographs, logs, scars, and legal filings pin events to the page so firmly that social systems can coordinate around what happened. Remove records, and the arrow blurs because stories can be contested without end. Strengthen records, and the arrow sharpens because consensus forms faster and holds longer. Institutions can cultivate healthy memory. Transparent archives, tamper evidence storage, and shared standards reduce the energy needed to agree on past states, which frees energy to plan. Education that teaches archival literacy immunizes the public against conspiracies that depend on memory holes. The future becomes navigable when the past is legible. Technology should respect both accuracy and privacy. Not every moment deserves eternal life, and some records must decay by design to protect dignity. Sculpted forgetting is as important as faithful remembering, and policy must balance them without giving either side absolute power. The arrow serves people when they can carry what matters and release what harms. For time machines of any kind, record stewardship is first principle. Devices that claim to bend timelines will fail ethically if they corrode trust in history. The wisest path bends time only after it strengthens memory. Time travel is not a door in our hands today. But every clock we have becomes sharper, every measurement deeper, every equation more honest. Which should ask us if we are asking, will we reach the future faster if we learn to manage time as a resource instead of returning to the past? What mistakes can we undo if we can bend entropy in local pockets? What new tests will law, economics, and ethics face when super-precise clock networks and quantum fault-tolerant architectures mature? Are the truly brave, not those who build today's measurement culture, archival discipline and feedback mastery, instead of waiting for wonders. In short, if we put together the levers that physics gives us instead of chasing magic, when a door opens tomorrow, we will already be ready to walk through it. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand this strangeness.